August 6, 1945. The United States drops an atomic bomb on the Japanese city of Hiroshima. 3 days later, they do the same in Nagasaki. The power of nuclear energy is demonstrated. Both cities and their populations are decimated. Out of the ruins of World War II, two superpowers emerge. The Soviet Union and the United States are now in a race to harness nuclear power.
The Cold War after 1950s was about the nuclear arms race. And the #1 driver in the nuclear arms race was technology.
It was an unprecedented militarization of both sides, which changed the perception of how much you can spend on defense.
Atomic and hydrogen bombs and intercontinental ballistic missiles. Nuclear power that fuels invention, weapons proliferation, and purpose beyond destruction. The Cold War, a decades-long struggle between two superpowers and former allies, the United States of America and the Soviet Union. But beyond the ideological divide of capitalism and communism was a battle of another kind, one for technological supremacy.
And for each of these systems, science and technology were critical for how they were going to thrive and grow and bring prosperity and justice for their people.
Experimentation with nuclear power, innovation of weapons technology, exploitation of science capabilities.
The entire space program, you could argue, was a creature of the Cold War.
A race for scientific supremacy that lifts humanity beyond Earth's atmosphere, drags the world to the brink of nuclear annihilation, and launches decades of research into scientific and engineering marvels that continue to define the modern world. (1945). War has raged across Europe for 6 long years. In January, the horrors of war are made real as prisoners from Auschwitz are liberated. In April, Soviet forces capture the German capital of Berlin. Italy's fascist leader, Benito Mussolini, is dead, executed by his own countrymen. Days later, Germany's leader, Adolf Hitler, takes his own life. By May, Germany surrenders unconditionally. The war in Europe is over. But in the Pacific, the fighting continues. Allied forces may have turned the tide against the once seemingly unstoppable might of Japan. But Japan does not surrender.
They're not allowing themselves to be taken prisoners. They're dying to the last man. So it looks like if you're going to invade the Japanese home islands, and that was the plan in September 1945, you might take 500,000 casualties.
Allied leadership determines that a swift and decisive conclusion is better than an ongoing and costly invasion of the Japanese mainland. The United States President, Harry Truman, sanctions the use of a new weapon, one that has been in development for the past 6 years. August 2nd, 1939. A letter arrives on the desk of then U.S. President Franklin D. Roosevelt, co-authored by fellow physicist Leo Szilard and signed by theoretical physicist Albert Einstein. The letter warns of Germany's advanced research into fission chain reaction.
It all begins with Einstein's letter. Now, a couple guys, particularly Leo Szilard, who's a Hungarian Jew, went to see Einstein at his home in Long Island. And the only way to capture the attention of the president in 1939 was have the most famous scientist in the world write a letter to the president, where he says the Germans have made a breakthrough here, and it's possible that because of the fission and the uranium to deliver great explosive power.
Just to give you an idea, one fission event produces 10 million times the energy of a chemical reaction.
Here, experiments with primeval atomic power led to the splitting of the uranium atom, force of the cosmic bomb.
Not every atom can undergo fission, only some can. And even for those that can undergo fission, it is often not a spontaneous reaction, but requires an initiating event. For instance, the absorption of a neutron. So if you get a heavy atom that's pretty much anything in the bottom half of the periodic table, and you throw neutrons at it, probability is that they will absorb the neutron. A small subset of those atoms, after absorbing the neutron, would decide to split in two, and that's fission. Uranium-235 and plutonium-239 are two such atoms that behave like that.
That such a bomb might be used against American targets, ports, cities, and military bases, persuades Roosevelt to fund a nuclear weapons research and development program, the Manhattan Project. In Lower Manhattan, in federal office buildings on Broadway and Chambers Street, U.S. Army Corps engineers begin coordinating the atomic bomb project. General Groves, the project's director, appoints a young physicist, Julius Robert Oppenheimer, to lead the project's secret weapons lab.
You couldn't invent these guys. You get General Groves, who built the Pentagon, very stern type guy, sort of an administrator. And he appoints a left-leaning American physicist, Robert Oppenheimer, is in charge of the project. You got all these left-wing guys who are being then poached by the American government to develop a nuclear weapon before anybody else does.
For added security, away from public scrutiny and prying eyes, the Manhattan Project transfers the lab to Los Alamos, New Mexico.
These guys are working 6-7 days a week. After a while, they're working around the clock. That is, they have different teams working on it. We got people in Tennessee working on the uranium. We got people in Washington State working on producing plutonium, and there isn't much of either one of them around. And they had something that the Germans didn't have. They had a blank check. And they had the best scientists in the world all concentrated in one place. And technological people, that is, people who could build bombs, started to work together, chemists, engineers, theoreticians, etc.
Once upon a time, men of science were preoccupied with the task of transmuting metals into gold. Now, we hope, the modern alchemists are proceeding with the job of using atomic knowledge for the benefit and not the destruction of mankind.
July 16th, 1945. The world's first atomic bomb is tested in the New Mexico desert. The result of the combined efforts of the United States, Canada, and the United Kingdom, the weapon, nicknamed the Gadget, releases an explosion the equivalent of 20,000 tons of TNT. The blast all but destroys the 30-meter-high platform from which it is dropped and creates a mushroom cloud that reaches 12 kilometers high. Just a few years after the Japanese attack on Pearl Harbor and Roosevelt's declaration that the United States enter the war, the atomic bombs born from the Los Alamos laboratory descend upon Japan. First in Hiroshima, then in Nagasaki. The bomb that explodes over Hiroshima is dubbed Little Boy, while the one dropped on Nagasaki is called Fat Man. Both deliver instant devastation on an unimaginable scale.
The two weapons relied on the same principle of trying to create a critical mass of fissile material in as little time as possible before it would detonate and explode into many pieces.
Little Boy is a 4,400 kilogram, 3-meter long, 70 centimeter in diameter gun-type nuclear weapon. Two separate portions of uranium-235, a target and a projectile, are fired into each other, triggering a chain reaction.
The bomb that was used in Nagasaki, also known as Fat Man, relied on an implosion type. In an implosion type device, you have a sphere of your fissile material that is surrounded by conventional explosives that are carefully arranged in such a way that if you detonate them all at the same time, they compress the sphere of fissile material and they get smaller and smaller and smaller at the point where it can reach critical mass. And in the middle of that sphere, you would have the initiator, which would start producing neutrons as it gets compressed. And the initial shock wave that compresses the plutonium sphere is also what stops it for a fraction of a second to explode out.
It is an atomic bomb. It is a harnessing of the basic power of the universe. The force from which the sun draws its power has been loosed against those who brought war to the Far East.
The destruction wrought by these new technologically advanced weapons is without precedent. In Hiroshima, 70,000 out of 76,000 buildings are damaged or destroyed. Civilian casualties are immense and continue to climb months after the initial explosions. August 15th, 1945. Emperor Hirohito announces the surrender of Japanese forces. The Second World War is over, and the atomic age begins.
They were defeated by modern science. So modern science allowed the Japanese a face-saving gesture to get out of the war. In the end, they were defeated by technology, and the lessons of that technological defeat carried straight through to the Cold War.
Will this power, now available to man, bring another, even more suicidal war upon us? Or can it be made to rule out war and open a new, progressive chapter of history, the atomic age?
The United States is now the sole superpower in control of this devastating technology. But power is always tested. The British, German, and Americans are engaged in nuclear programs years before the US bombing of Hiroshima and Nagasaki. So too is the Soviet Union. Soviet leader Joseph Stalin had been convinced by Russian physicists of the necessity of pursuing the development of a uranium bomb.
The explosion of American nuclear bombs in Hiroshima and Nagasaki caused the Soviet Union to begin a crack program to produce its own nuclear weapon. The design was stolen by Russian Soviet spies.
Though minuscule when compared to the Manhattan Project, the Soviet program accelerates in the years after the conclusion of the Second World War.
You know, at the end of the war, the Soviets grabbed as many scientists as they could, German scientists. So, you know, they knew as much about splitting the atom as anybody else did. The trouble is, would they have the technological ability to do something about it?
The problem was not so much the design as the creation of an industry that could produce arms-grade uranium, arms-grade plutonium, and a lot of other components that are needed to make a practical nuclear weapon.
Under the direction of physicist Igor Kurkatov, the Soviet program to develop an atomic bomb operates out of Laboratory No. 2 on the outskirts of Moscow. The program grows rapidly with the onset of the Cold War, expanding from 650 staff in 1946 to 1,500 in 1947. Secrecy is paramount. Documentation lists the lab as an assembly workshop, and employees are subject to complex security checks. August 29, 1949. The Soviets detonate their plutonium-based implosion-type atomic bomb, the RDS-1, also known as First Lightning, at their testing ground in Kazakhstan. A 22-kiloton yield delivered in the blink of an eye. September 3rd, a U.S. Air Force B-29, specially fitted with filters designed to detect radioactive debris, travels from Japan to Alaska. It detects levels of radioactivity marginally above the threshold that would dictate further investigation. More samples are collected. They reveal an unsettling truth to the international intelligence community. A Soviet nuclear test has taken place.
After the discovery of Soviet nuclear capability in August 1949, forced the Truman administration to think about how to move forward in the future. And most importantly, it was the end of American nuclear monopoly. So then we enter a new stage.
The stunning news bursts on America. John Q. Citizen wonders what happens now.
April 14th, 1950. President Truman receives National Security Council Paper No. 68, a document that will go on to shape U.S. Cold War policy for decades.
It's a document written by Paul Nitze, who was the co-author of the Strategic Bombing Survey after World War II. Nitze argues Soviets had probably acquired a nuclear weapon, and then he says something very important that did not change for the entire Cold War. He says once they have a chance to deliver this, they will. So he always argued that once the Soviet Union had acquired a certain technological superiority, they would use it first.
And so the point of NSC 68 was to say we have to fight this war in every possible way that we can and build up our arsenal in every possible way that we can, precisely so that we don't have to use it.
as communism continues to gain a foothold in China and Korea. The fear Americans have of Soviet communist expansionism is palpable.
And so this document's actually going nowhere until the North Koreans attack the South Koreans, which makes all the people behind NSC 68 look like geniuses because they say the Soviet Union is probing, waiting for the right moment.
June 25th, 1950. Troops of the North Korean People's Army crossed the 38th parallel into South Korea, starting the first military conflict of the Cold War.
I think it's also worth noting that the Cold War was anything but cold. Imagine telling that the Cold War was cold to the inhabitants of Vietnam, Korea, Afghanistan. These people knew full well that the Cold War was also a stage for seeing out a series of hot military action.
The North has support from the Soviet Union and Chinese Communist forces. South Korea is backed by a United Nations force comprising mostly of the United States military.
If the United Nations yields to the forces of aggression, no nation will be safe or secure. If aggression is successful in Korea, we can expect it to spread throughout Asia and Europe and to this hemisphere.
After South Korea is attacked, NSC 68 becomes a policy. That is, the word goes out that this is what we're going to follow. And it becomes the most formative, seminal national security paper ever written because it controlled how the money was going to be spent for the next 10 or 20 years, particularly getting a thermonuclear weapon.
Truman directs scientists of the Los Alamos facility to focus their attention on a weapon that would make the death toll in Hiroshima and Nagasaki appear minuscule by comparison. The hydrogen bomb is coming. Atomic bombs use uranium or plutonium and rely on fission, the nuclear reaction that cleaves an atom in two and triggers the chain reaction. Hydrogen bombs similarly use uranium or plutonium in the first phase of the reaction, but additionally harness the intense heat generated by this to trigger a second phase, which fuses hydrogen isotopes deuterium and tritium to create helium.
The challenge here is that the two atoms that you start with are repelled by the positive charge inside them. So you have to accelerate them to incredible energies in order for them to collide and not bounce around as they normally would, but actually overcome the repulsive force and then fuse together. The amount of energy that can be released through fusion is really quite large, but it is technically much, much harder to achieve enough energy to initiate the reaction. So in the case of a weapon, the starter for a hydrogen bomb is actually a nuclear bomb. So in the same way that a nuclear bomb uses conventional explosion to start it, in a hydrogen bomb use conventional explosions to start a nuclear bomb, which then produces enough energy to start a fusion bomb. The yield of a fusion bomb is much, much greater than that of a fission bomb, and I can only say we are lucky we've never seen the effects of a fusion bomb on a human population.
The United States hope this weapon will reinstate their lead in the nuclear race. November 1st, 1952. The first hydrogen bomb is tested near a South Pacific atoll in the Marshall Islands as part of Operation Ivy. A thermonuclear explosion 1,000 times more powerful than the bomb that destroyed Hiroshima. And they don't stop there. Over the next few years, the United States continue thermonuclear tests in the South Pacific Marshall Islands.
With nuclear weapons research, the emphasis was always on speed. The emphasis was on yield. The emphasis was on damage. It was never on safety. And for the Atomic Energy Commission, the organization that ran the atomic tests, the consensus was that whatever damage there was, the risks of damage from fallout were less than the risks of losing to communism, were less than the risks of nuclear war.
Operation Ivy is followed by Operation Castle, a series of 6 tests, the largest of which, Castle Bravo, fueled by lithium deuteride, explodes with a yield of 15 megatons.
The yield of this bomb was much larger than the United States had anticipated, so much so that Marshall Islanders could never return to their homes.
There were 2 mistakes on that day. Number 1, the test was much greater than they thought it would be. In fact, it sank the island that it was tested on, sank all the damn equipment. And the second thing is the wind was blown in the wrong direction. It created a great deal of radiation in the ocean.
The effects of the blast travel much further than anticipated, and the unfortunate crew of a Japanese fishing trawler called Lucky Dragon, some 128 kilometers from the site of the test, also experienced radiation sickness.
When the public saw what had happened, the Atomic Energy Commission denied that there was any damage and said, no. Fallout is safe. Nuclear testing is safe. But 1954 was really the first moment that the public at large said, we don't trust you, we don't agree with you. Nuclear testing is not safe.
While the successful testing by the United States of thermonuclear devices momentarily restores a sense of security for the American people, in August of 1953, the Soviets pull that rug out from under them. They conduct their own nuclear tests, one of which, RDS-6, consists of alternate layers of hydrogen fuel and uranium. Its design is inspired by the layered design of a puff pastry, Slaka. With a yield of 400 kilotons, the test is more powerful than previous Soviet tests, but falls short with American comparisons. But this proves the Soviet Union is still in the race, with a deliverable weapon that can be deployed from a plane. Throughout this, the Korean War continues, a costly campaign languishing between stalemate and negotiation. It had been U.S. President Harry Truman that ordered U.S. air and naval forces to repel the North Korean invaders. But by 1953, he is out of office, and Dwight D. Eisenhower is sworn in as the next American president. Eisenhower indicates to his administration a readiness to use nuclear weapons to break the deadlock in Korea, if required.
Eisenhower made it very clear that he would use nuclear weapons, and that scared the hell out of a lot of people, because if you're going to use nuclear weapons against a superior conventional force, then what's the bottom line there?
Man's greatest scientific achievement, therefore, cannot yet be made exclusively to serve the advancement of man's welfare and happiness. Instead, we are forced to concentrate on building such stores of armaments as can deter any attack against those who want to be free.
March 5th, 1953. Soviet leader Joseph Stalin dies, creating a power struggle within the Communist Party. One that Nikita Khrushchev ultimately wins when he is named as first secretary of the party in September. While the Soviet Union has been providing material support to North Korean and Chinese forces, this is no longer necessary by the time Khrushchev comes to power. July 27, 1953. The Korean Armistice Agreement is signed, bringing an end to hostilities. The conflict may have ended without the deployment of nuclear weapons, but it awakens in North Korea a desire to build and proliferate their own nuclear weapons program. As the arms race continues, both sides look to increase their nuclear capabilities by developing improved delivery systems.
The problem was, how do you strike the Soviet Union with anything other than a manned aircraft?
Short-range ballistic missiles launched within Earth's atmosphere are one way of delivering a nuclear warhead from afar. While intercontinental ballistic missiles, or ICBMs, travel into Earth's suborbit, allowing for the potential of even greater striking distance.
The advent of the ballistic missile allowed the United States, also allowed the Soviet Union to strike targets rapidly, and then over time to strike those targets very accurately as well.
This ability to launch nuclear warheads from great distances is something the Soviet Union believes is vital to their national security.
Well, Russians developed their own nuclear weapon that took some years, but it was developed. Then there was a problem of delivery systems. And Russian bombers would have a hard time reaching the United States. So that means the Soviet Union began investing heavily into building intercontinental missiles.
Both the Soviet and American long-range ballistic missile programs evolved from the German V-2 liquid propellant rockets of World War II. August 21st, 1957. Soviet scientists conduct the first successful launch of the R-7 Semyorka, the world's first intercontinental ballistic missile. 34 meters long and about 300 tons in weight, the R-7 is powered in stages by rocket engines that mix liquid oxygen with kerosene. 4 RD-107 rocket boosters achieve the initial launch. A central RD-108 engine maintains power through the first and into the second launch stage. Smaller rocket engines, vernier thrusters, adjust for maneuverability, stability, altitude, and velocity. The missile's trajectory is guided by radio control.
The Semyorka was important. It was the first intercontinental ballistic missile ever deployed, but it was not really an ICBM of any practical purpose. As an ICBM, it was soon scrapped because it used liquid oxygen, and that means you couldn't keep it for a long time ready to go. And also you couldn't put it into a silo. It was standing just in the open. That means very vulnerable.
In missile technology, the R-7 Semyorka is a first for the Soviets in the Cold War tech race. This successful launch comes a month before the US successfully tests their Atlas ICBM, a program that has been running concurrently to that of the Soviets.
Project Atlas was the program to field the first US intercontinental ballistic missile. And that meant that it was a program to do something that had literally never been done before. Take a missile, launch it up through the atmosphere where it was experienced shaking, heating, out of the atmosphere as the Earth orbited underneath it, and then have the re-entry vehicle re-enter the atmosphere, and to get that payload to land somewhere close to where it was intended.
The project is given unprecedented funding and becomes the nation's highest research and development priority, costing an estimated $8 billion.
President Eisenhower made clear that money was not an object, but time was of the essence. And so as a result, all the different parts of the Atlas had to be developed in parallel. So Project Atlas was a huge effort in not just developing new technology, but also integrating those different technologies.
Both Cold War superpowers now have intercontinental ballistic missiles that can deliver nuclear weapons, thermonuclear warheads, chemical or biological weapons. Inspired by the German V-2 rocket, variations continue as designs and modifications evolve. Missile technology now fuels these Cold War adversaries to greater heights. In October of 1957, the world's first satellite, Sputnik, is launched into space by a variation of the R-7 Semyorka. The United States is beaten into space, underestimating the Soviet Union's technological prowess. The world and Eisenhower are caught off guard.
There was an enormous amount that we didn't know about the Soviet Union and its arms programs during the early Cold War. And so when the Soviets launched Sputnik, the first satellite, there was concern that the Soviets had a real lead in missile technology.
Modern weapons like this tell the story of Russia's striking power.
America now takes seriously Khrushchev's declaration that the Soviet Union possesses significant nuclear capabilities.
Khrushchev talked about the Soviet Union turning out ballistic missiles like sausages as a way of hyping their missile program.
Some within the Eisenhower administration are convinced that the United States has a missile gap, that the Soviets have proliferated a nuclear arsenal far exceeding their own. But now, the United States is ready to show off their latest development in missile technology, one that will level the playing field and reassert their Cold War supremacy. February 1st, 1961. The intercontinental ballistic missile, known as the Minuteman, is tested at Cape Canaveral. A 3-stage solid-fuel-burning missile that soars up out of Earth's atmosphere, maintaining a celestial suborbital arc, before returning to swoop back down fast toward its target.
The first generation of intercontinental ballistic missiles, like the Atlas and like the Titan, were liquid-fueled. It took a while to actually put the fuel in the missile, to raise it up, to prepare it for launch. The Minuteman was designed to be fired right away. So the Minuteman was the first ICBM to feature solid propellant, which meant that it was propellant that was stored in the missile itself. And so it was designed for rapid fire.
If needed, they would launch from underground missile silos built across the Great Plains of Central and Northern America. 1,000 metallic beasts standing primed. A hibernating, weaponized herd, ready to launch in an instant. It arrives just in time for the Cuban Missile Crisis. November 1960. President Eisenhower's second term in office comes to an end. His Republican Party successor, Richard Nixon, faces off against an energized young Democrat candidate by the name of John Fitzgerald Kennedy. Kennedy's campaign promises include a more aggressive stance on winning the space race and pursuing nuclear non-proliferation. November 8, 1960. Kennedy wins the election in a close race to become the 35th President of the United States. However, before Kennedy conquers the tech race into space, a threat to America emerges in the form of Cuban leader Fidel Castro. Castro had overthrown the military dictatorship ruling Cuba and nationalized all US-owned property, prompting the severing of diplomatic ties and a trade embargo from the United States. Cuba, located less than 200 kilometers from the American mainland, looks towards the Soviet Union for economic and military support. April 17, 1961. Kennedy approves an invasion of Cuba by over 1,000 CIA-trained anti-Castro Cuban exiles. Kennedy hopes that by overthrowing Castro, he will remove an emerging communist state from America's doorstep and gain an important advantage in the Cold War. The invasion of the Bay of Pigs is both a miserable failure and a turning point in the Cold War. It widens the chasm between America and Cuba, while strengthening Cuba's relationship with the Soviet Union. By the time the Bay of Pigs occurred, America has nuclear weapons installed at bases in Turkey and Italy. The Jupiter, medium-range ballistic missiles armed with a 1.44 megaton thermonuclear warhead, could scorch through the sky and reach all of the Western USSR, including Moscow. The geographical proximity of these weapons facilities so close to Russia does not sit well with Khrushchev.
A decision was made to deploy some combat troops to Cuba and nuclear missiles. Having Cuba as a launching pad for Russian Soviet missiles seemed very important militarily, that this was a game changer, changing the nuclear balance, giving the Soviet Union a handle on the American nuclear superiority.
Cuba wants to prevent another Bay of Pigs invasion. With Kennedy now in office, American U-2 spy planes fly over Cuba and capture the construction of medium and intermediate range ballistic missile facilities.
At United Nations headquarters in New York, the Cuban crisis is the one and only subject of discussion.
Let me ask you one simple question. Do you, Ambassador Zorin, deny that the USSR has placed and is placing medium and intermediate range missiles and sites in Cuba? Yes or no? Don't wait for the translation, yes or no?
Khrushchev argues that like US missile facilities in Italy and Turkey, the presence of Soviet missiles in Cuba is merely a deterrent to American aggression. But Kennedy won't allow it.
The fear during the Cold War is that either side would have a technological breakthrough which would become destabilizing. That is, the other guy would be so convinced that the other guy was going to strike first, that they might strike first.
Robert McNamara, Kennedy's Secretary of Defense, advises the newly elected president that 3 options exist. 1. Engage diplomatically with Cuban leader Castro and Soviet leader Khrushchev. 2. Encircle Cuba with a naval quarantine, stopping Soviet ships from entering Cuban waters. 3. Decimate the missile sites by air attack, but risk triggering a Soviet counterattack.
They believed that the United States in '62 had such a nuclear advantage that any nuclear war, America would win. America would also be hit by nuclear weapons, but would survive while the Soviet Union would be obliterated. President John Kennedy didn't want that, and the Secretary of Defense McNamara also didn't.
Intermediate-range ballistic missiles can span a distance of between 3,000 and 5,500 kilometers, roughly 2,000 to 3,000 miles. Medium-range ballistic missiles generally range less than 3,200 kilometers. Clearly, the medium-range Soviet SS-4s that had been photographed by the US being assembled in Cuba, and the intermediate-range Soviet-built R-14 missiles could reach any target within the United States. Fear of nuclear attack is more real than ever before.
What are you supposed to do when you see the flash? Duck and cover. Duck and cover. Duck.
October 22nd, 1962. Kennedy announces to the American people the presence of Soviet missiles in Cuba.
It shall be the policy of this nation to regard any nuclear missile launched from Cuba against any nation in the Western Hemisphere as an attack by the Soviet Union on the United States, requiring a full retaliatory response upon the Soviet Union.
The American public, fearing a nuclear war is imminent, rush to hoard food and gas and find ways to protect themselves from an atomic blast. Across the Great Plains of southern and northern Dakota, Wyoming, and Montana, the Minuteman missile silos power up. The situation is spiraling out of control. Both sides send demands to the other to end the dispute. Castro encourages Khrushchev to attack the United States. October 27th. Khrushchev and Kennedy finally reach an agreement, ending a crisis that brought humanity closer to destruction than ever before. If Kennedy promises not to invade Cuba and remove missiles from bases in Italy and Turkey, Khrushchev will dismantle the Soviet missiles and withdraw from Cuba.
The missile crisis was seen as a Russia stepping down. The Americans also withdraw their missiles from Turkey, but that was agreed that withdrawal will be kept secret. So from the public point of view, it was that President Kennedy stood up to Khrushchev, which was an important factor in his overthrow that happened in 2 years in '64, when there was a kind of conspiracy and coup to remove Khrushchev, that he turned out to be weak in the Cuban Missile Crisis.
The Cuban Missile Crisis is a turning point in the Cold War. Tension eased, communication prevailed.
So they found a compromise, and the Russian missiles were withdrawn from Cuba, and the nuclear weapons with them, which was a big deal at the time, though in several years the Soviet Union developed and began mass production and mass deployment of silo-based ICBMs, so they didn't really need Cuba anymore militarily that much.
August 5th, 1963. After years of discussion, the Soviets, Americans, and Great Britain take the first step toward nuclear arms control by signing the Partial Test Ban Treaty. It comes at a time when nuclear testing had reached a peak. Previously, on October 30th, 1961, the Soviet Union had tested their RDS-220 hydrogen bomb. The 8-meter-long, 2-meter-in-diameter multi-stage thermonuclear weapon was so large it had to be carried in a specially modified bomber to conduct the test. While similar in shape to the Fat Man and Little Boy bombs, it is estimated to be 1,500 times more destructive than the two combined. Deployed by a parachute, the bomb detonated 3.9 kilometers above Novaya Zemlya, an archipelago in the Arctic Ocean, leaving a mushroom cloud 67 kilometers high. The Partial Test Ban Treaty assures that a bomb this powerful cannot be tested again.
And the Soviets and the Americans are willing to agree to this, along with the Brits, in 1963. And I had a chance to talk to the top American negotiator. And I said, why now? And he said, well, after all the nuclear tests and the three-stage rocket tests in the 1950s and early 60s, the United States knew everything it knew about atmospheric testing, and so did the Soviet Union. So what they agreed to do was to just put it off the table, because they knew everything they had to know.
As the Cold War rolls on, other nations look to enter the arms race by developing their own weapons programs. Initially, the People's Republic of China looked towards their communist ally to kickstart their nuclear research.
The Soviet Union provided technology and know-how to help China develop their nuclear weapon. So that's happened in many cases. Technology exchange with China stopped when under Nikita Khrushchev, when China and Russia became bitter enemies, especially during when China had this border war with India. And by '62, I understand all technological transfer stopped.
As China distances itself from the Soviet Union, the Cold War morphs from a bipolar Soviet-American affair to a tripolar Soviet-American-Chinese standoff. The Chinese were invited to put their signatures on the 1963 Test Ban Treaty, but they declined. In 1964, China tests their first nuclear weapon. Project 596, codenamed Sheik by US intelligence agencies, is a uranium-235 implosion fission device.
Now, the Chinese were very reluctant to acquire nuclear weapons, and the ones that they have today, the ones they developed during the Cold War, were designed what they thought to be a minimum deterrent. What is a deterrent? A deterrent is fear of retaliation.
About 2.5 years later, China tests their first thermonuclear device. Codenamed Test Number 6, this hydrogen bomb was detonated in a dried-up salt lake, Lop Nur. Like China, France too had not signed the Test Ban Treaty. From 1960 on, France conducts over 200 nuclear tests in French colonies outside of Europe, such as the Algerian Sahara and French Polynesia in the South Pacific. Through the 1960s and into the 70s, nations raced to keep up pace with nuclear weapons development. Countries such as India and Pakistan, beleaguered by border disputes or ongoing tensions, continue to develop their own nuclear weapons profile. They, and countries like Israel and North Korea, chose not to commit to the NATO-negotiated 1968 International Non-Proliferation Treaty. Nuclear arms are embraced by countries whose economic, political, and social landscape has altered and grown in the decades following the Cold War. The world is changing. In the wake of environmental catastrophes triggered by nuclear testing, the public is keenly aware of the dangers of nuclear technology. Still, nuclear-powered technology developed during the Cold War becomes an energy source that nations clamor to tap into. Nuclear reactors can provide countries with a zero-emission clean energy source.
A nuclear reactor can really be thought of as an enormous boiler or a kettle. Its sole purpose is to heat up water. Once you have hot water and you can generate steam, it works the same way as any other thermal generator. In the core of the nuclear reactor, you have nuclear fuel in the form of little uranium dioxide pellets. And you have hundreds of those stacked into nuclear fuel pins, which are about the width of your little finger and 4 meters in length. Hundreds of those fuel pins are then assembled in nuclear assemblies, and hundreds of those assemblies are placed inside the core. In between all these fuel pins and the fuel assemblies, there is space for water to go through. As the water rushes in between them, it extracts the heat that is generated inside the nuclear fuel from fission. So the water is never directly in contact with the nuclear fuel. It is separated by a metal thin tube, the nuclear fuel pin, but it extracts the heat that is generated inside the fuel. Once the water becomes hot, you can raise steam with that water, and then the rest is the same.
But when technology fails, or radiation remains in the atmosphere, the fate of millions are thrown into jeopardy. March 28, 1979. A malfunction occurs at the 3 Mile Island nuclear power station near Harrisburg, Pennsylvania. No deaths or serious injuries are attributed to the meltdown at 3 Mile Island, but it was a warning of worse to come. Less than a decade later, another high-profile accident occurs, this time at the Chernobyl nuclear power plant in what was then the Ukrainian Soviet Socialist Republic. April 26, 1986. A routine safety test is carried out to determine how long cooling systems will continue in the event of a reactor shutdown before supplementary power is restored. As the operators conduct their test, they decrease reactor power to a level that quickly renders the RMBK Soviet reactor unstable.
Even in the day, at the time, most of the world had criticized the reactor for being unsafe. It was known that under certain conditions, admittedly fairly obscure operating conditions, the reactor could be unsafe. It didn't have those natural feedback mechanisms, which are laws of physics that we rely on to achieve a controlled chain reaction. And that's exactly what happened the day of the accident. The operators had removed all sorts of safety features, had done lots of things against protocol, had done things that were thought actually unthinkable of, such as removing every possible control rod from the reactor. But yet that was allowed. A proper reactor design should never allow for that to be possible.
As the core begins to melt, tons of radioactive waste billows into the atmosphere. 2 Chernobyl operators die that day. 130 workers and first responders are hospitalized with radiation. 28 die in the days soon after. 14 die later from radiation-induced cancer. 120,000 people are displaced in the immediate aftermath. A spike in childhood thyroid cancer follows. 4,000 deaths in Soviet states and between 9,000 to 15,000 deaths across wider Europe were attributed to Chernobyl. The disaster and resulting political fallout is later described by Soviet leader Mikhail Gorbachev as one of the factors in the dissolution of the Soviet Union.
There is agreement, however, on both sides of the nuclear argument post-Chernobyl. It must never happen again.
The Cold War kick-started a battle for technological dominance between 2 superpowers, igniting the nuclear age.
The Soviet Union and the United States were engaged in the Cold War, which began as a political and ideological struggle. By the time it was over, the United States and the Soviet Union had created 98% of the nuclear warheads.
Since the conclusion of the Second World War, the United Nations has estimated that as many as 130,000 nuclear weapons have been built. A power balance that continues to shape the global political landscape long after the Cold War thawed.
The number of strategic nuclear weapons has been limited and decreased by all these treaties, and so right now we're maybe 10 times lower than we were in the end of the Cold War. That's a good thing. Although, on the other hand, maybe not so good, because this makes nuclear war more plausible, because when both sides together had about 70 to 80,000 nukes, everyone understood that when such a number of nukes are actually detonated in different parts of the world, that's the end of it.
So what I liked about the Cold War is everybody had the same playbook. They could see the futility of nuclear weapons. So I think nuclear weapons stabilized the Soviet Union and the United States at the end for them to get rid of the arms race, and it probably prevented the outbreak of a general nuclear war or World War III.
Nuclear power fueled the ideological battle for supremacy. It helped launch humanity into space and unleashed a potential energy solution for the future. And it made us certain that above all else, mutually assured destruction is something we must strive to avoid. In the Cold War, a new age of innovation dawns. Fields of science and technology flourish like never before.
Really, for both the United States and the Soviet Union, both of these countries saw science and technology as critical to winning the Cold War.
Military-funded programs loop science and technology into a self-perpetuating industrial complex, meshing government, military, and weapons manufacturing.
All industry was built double use with a military capability inbuilt.
And science is welcomed into the corridors of power.
So it wasn't just the number of bombs that you might have, but the numbers of PhDs that you might have in a certain field.
The Cold War, a decades-long struggle between two superpowers and former allies, the United States of America and the Soviet Union. But beyond the ideological divide of capitalism and communism was a battle of another kind, one for technological supremacy.
And for each of these systems, science and technology were critical for how they were going to thrive and grow and bring prosperity and justice for their people.
Experimentation with nuclear power, innovation of weapons technology, exploitation of science capabilities.
The entire space program, you could argue, was a creature of the Cold War.
A race for scientific supremacy that lifts humanity beyond Earth's atmosphere, drags the world to the brink of nuclear annihilation, and launches decades of research into scientific and engineering marvels that continue to define the modern world. At the height of the Cold War, Soviet and American adversaries pursue the militarization of the science and technology industries.
Both the United States and the Soviet Union saw the Cold War as an ideological conflict between capitalist liberal democracy on the one hand and communism on the other. And so for each of these ideologies, science and technologies played critical roles in ideas about progress and justice and development. So under capitalism, you needed science and technology to drive economic development, and you also needed it as a system of rationality that would help voters make decisions and policymakers make choices. Under communism, ideas about science and technology were thought to drive a kind of progress that would allow all the people to benefit from the wonders of the future and from the wonders of modernity.
Cold War machines of war now travel faster, for longer, beyond the Earth's atmosphere and deep into the ocean. The nuclear age explodes with ferocious magnitude as governments raise the stakes, placing greater value on the role of science and technology in the war domain.
At the end of World War II, the leaders of the Allied countries really credited their success to scientific and technological achievement. Of course, the atomic bomb, but also things like radar and the proximity fuse. And so when they looked at everything that they had accomplished, and they looked at what the countries who had lost hadn't accomplished, they said, this is the difference. And they assumed that winning the Cold War was going to require the same kinds of technological and scientific insights.
July 1945. Vannevar Bush, director of the Office of Scientific Research and Development, sends a report to the US President Harry Truman titled Science, the Endless Frontier.
This document worked from the assumption that scientific and technological achievement came from basic research. And so it argued that the United States should set up some kind of research system that funded basic research driven by, led by scientists, and that would lead to applications that would improve the quality of life for all Americans, that would drive economic growth, and that would keep the country safe, that would build military technologies as well.
Many ideas in his report helped lay the foundation for the creation of the National Science Foundation in 1950.
And they were convinced that this scientific research had to be driven by scientists, not the government, not military leaders. Now, in the post-war period, politicians didn't necessarily agree with that. And, this is a legitimate question. Were scientists running the show? Or were scientists available as advisors to answer the questions that they were asked and to only answer the questions that they were asked?
Despite this tension, politicians and scientists soon discover how mutually beneficial they are to each other. One such way is showing an increasingly distrustful public that atomic energy can be used for more than mass destruction.
The United States had a problem in the 1950s, which was that at the same time that it was trying to say it was the best proponent of scientific cooperation, its nuclear testing operations were coating the Earth with fallout. And so people were increasingly not trusting the United States.
If the public see that nuclear detonations yield societal, agricultural, or economic benefit, they might sooner accept continued nuclear weapons development and testing. September 1st, 1958. The Second United Nations International Conference on the Peaceful Uses of Atomic Energy, better known as the Atoms for Peace Conference, convenes on the shores of Lake Geneva.
The peaceful aims of the conference were naturally stressed by Mr. Hammarskjöld, United Nations Secretary General, proof that the nations can cooperate in this atomic age.
At the conference, several thousand observers, government officials, and scientists from the East and West meet to discuss the potential of using nuclear energy for peaceful purposes.
The United States wanted to send fissile materials, to share fissile materials with other countries, with the idea that the Soviet Union would also be required to contribute fissile materials to a kind of nuclear bank. This would simultaneously reduce the amount of fissile materials that the Soviet Union could use in its own nuclear weapons, but it also would show that the United States was a partner, that you could use radioisotopes in medical research. Maybe you could use it to drive agricultural research, to create new breeds of plants. You could build nuclear reactors and have electricity too cheap to meter, that the atom could be a source of bountiful good as well as this terrifying object.
As part of the Atoms for Peace program, the U.S. exports over 25 tons of highly enriched uranium to 30 countries to fuel research reactors. Critics of the program argue that this could lead to increased international nuclear proliferation. The U.S. hoped that the immediate benefits outweigh any future negatives. As nuclear experimentation continues through the Cold War years, the Soviets and Americans became aware of a growing necessity to show the public that nuclear detonations can benefit industries and economies.
Today, this scene of preparation for a peaceful nuclear explosion is at an experimental site. Tomorrow, when the potential of nuclear explosives is fulfilled, this scene will move to the site for a new harbor, canal, or mountain pass, a mine, oil field, gas reservoir, or water storage basin, or perhaps a new underground laboratory.
Originating in June 1957, the United States program Project Plowshare detonates 31 nuclear warheads in 27 different locations.
This is the peaceful potential of nuclear explosives that the United States is developing for all mankind. In the program it calls Plowshare.
In one case, an explosion displaced 12 million tons of earth, sending a radioactive cloud of dust that rises 3.6 kilometers high as it travels in the direction of the Mississippi River. In the Soviet Union, their peaceful nuclear explosion program is divided into two projects with a total of 239 tests and similar objectives to that of the US. The largest detonation in January 1965 creates a 100-meter deep, 8,000-acre conical crater called Lake Chegan. The explosion sends a radioactive cloud into the atmosphere so large it is eventually detected in Japan. To this day, Lake Chegan remains radioactive. Peaceful nuclear explosion programs did little to assure public concern that nuclear power was anything but fuel for destruction. As protests regarding the testing of nuclear weapons continue, the United States looks to a growing scientific field to help with another technological problem: how to monitor and enforce nuclear test ban treaties. For this, they look to seismology, a scientific field that is transformed by the Cold War.
The thing about arms control agreements and testing agreements is the other guy lying about it? Is he testing nuclear weapons underground? So a lot of times, seismology was used to test the waves underground to see if they were using thermonuclear weapons or what you're up against.
One program supported by the influx of federal support for seismology is Project Vela, designed to develop new technologies to detect nuclear explosions in anticipation of a partial test ban treaty.
By electronic instrumentation, surface and subsurface measurements were made of violent shock effects in the immediate vicinity of the deeply buried explosion.
Project Vela includes seismic monitoring and a nuclear testing detection satellite program for the Earth, atmosphere, and outer space. August 5, 1963. The United States, United Kingdom, and Soviet Union sign a partial test ban treaty in Moscow. It prohibits the testing of all nuclear weapons, but excludes those conducted underground. October 1963. Vela Uniform begins as part of Project Vela. It aims to develop America's nuclear weapons detection capabilities by conducting experiments to differentiate underground nuclear tests from other seismic events, such as earthquakes.
Seismology was sort of dragged into the arms race, what we call the verification angle. You can only verify a nuclear weapon two ways. Pick it up in the air, that is, you can pick up the radiation, or you can measure it with seismology under the ground.
As a consequence of the Americans and Soviets seeking to find stable ground with the Test Ban Treaty, the field of seismology explodes. Funding pours in throughout the decade to the tune of $250 million. 1965. U.S. seismologists develop a system of linked seismometers, the Large Aperture Seismic Array. 525 seismometers distributed along geometric patterns, covering 25,000 square kilometers and using digital signals to transmit data, filtered and processed on high-speed computers. The Large Aperture Seismic Array's first objective is to detect, identify, and locate secret underground nuclear explosions. 120 data-sharing stations throughout 60 countries establish the worldwide standardized seismograph network. Seismology stations had been operational before this network was built, but now Cold War technology makes data collection more accurate. Directionally oriented seismographs, synchronized by crystal-controlled timepieces, feed seismograms onto photographic drum recorders. The American system is hailed as the finest system of global monitoring, but still lacks Soviet and Chinese data. The Soviets and their allies have their own network, the Unified System of Seismic Observation, in excess of 100 stations equipped with a variety of comparable seismic and data-sharing systems. Seismological technology adapted from the Cold War remains a constant presence, eavesdropping on the rumblings of today's Earth. In 2017, seismic data registered a nuclear explosion 16 times larger than the atomic bomb dropped on Hiroshima, one in a multitude of underground nuclear tests that North Korea has conducted since 2006. The field of seismology seized an opportunity to flourish during the Cold War. Another discipline taking the opportunity provided by increased funding into the sciences aims to increase the understanding of the Earth and its atmosphere. Meteorology. Advancements in the study of the Earth and global weather patterns grew out of the International Geophysical Year from 1957 to 1958.
This was a program that involved nearly 70 countries, large and small, very different levels of development, who were going to cooperate to gather information about the natural world. Things like the exact shape of the Earth, or maybe information about the magnetic sphere. Not coincidentally, many of these ideas could also be useful for national defense, which is one of the reasons that the United States encouraged it.
The International Geophysical Year was an important opportunity to begin making use of relatively new systems that were being refined, that had hot war significance and Cold War significance. And so you have systems like radar and radioactive tracers and computers, sounding rockets and satellites. All of these are dual use, both in the sense that they're military and civilian, but also in the sense that in learning how to better operate this equipment, you can learn more about the world around you.
Meteorologists within the United States Weather Bureau, such as Dr. Harry Wexler, had long championed the development of satellites to aid weather forecasting. Synoptic meteorologists hope that the use of television and infrared cameras placed on satellites orbiting the Earth will provide images of cloud cover, allowing more accurate predictions of weather fronts and warning of major weather events, such as cyclones. Yet, it is military advancements in Cold War reconnaissance satellites and an increase in funding of programs as part of the International Geophysical Year that ultimately make the world's first meteorological satellite, the Television Infrared Observation Satellite, or TIROS, possible.
The TIROS satellite had its roots in Army reconnaissance satellite capability. The infrared and the photographic capability have been developed by RCA and the Army Signal Corps after the launch of Sputnik and during the US's reevaluation of the Armed Service Space programs and consolidating it under the Advanced Research Project Agency, ARPA. they decided that they didn't need this extra reconnaissance satellite because the Air Force was already working on a highly classified reconnaissance satellite program. And so in response to that decision, colloquially, it's said that Wernher von Braun said, "So we'll look at the clouds."
April 1959. NASA takes over the TIROS project and gives the responsibility of analyzing data gathered by the satellite to the Weather Bureau. April 1st, 1960. NASA launches TIROS-1.
TIROS-1, which stands for Television and Infrared Observation Satellite, marks a new adventure in space, weather observation.
The satellite is 48 centimeters high, 106 centimeters in diameter, and weighs 122 kilograms. 9,200 solar cells cover an aluminium alloy and stainless steel body. On board are two 15-centimeter-long television cameras, one a lower resolution wide angle, and the second a higher resolution narrower angle. While only operational for 78 days, the 22,952 pictures produced by the satellite provide the first look at the Earth's cloud patterns from space, and are a vital step in the future development of monitoring global weather conditions.
Part of the significance of TIROS-1 was also determining exactly what could be seen from space and how detailed the images actually would be through the atmosphere, through clouds.
Despite the successful launch, politics hamper the goal of a true worldwide weather monitoring and communication system. In Cold War thinking, if observation satellites could capture scientific data, they might similarly track human activity.
There was concern that the images might actually be too detailed. The United States was already planning on circulating, they called them NEF analyses, the photographs that they would take of cloud cover. And so the release of the NEF analyses were actually delayed with TIROS-1 and 2 so that the United States could make sure that this was information that could go out. Another element of TIROS-1 and 2 is that they were launched in orbital inclinations that did not go over the Soviet Union, so that the Soviet Union wouldn't have concerns about this being a spy satellite.
As improved TIROS satellites are launched, global weather patterns are captured and transmitted to meteorological ground stations on Earth.
TIROS-9 was put into a nearly polar orbit over the rotating Earth so that it can photograph the entire world each day. The satellite was programmed to take 400 pictures daily. Each day's coverage is converted to NEF analysis maps, which show the storm fronts all over the world. These are made available to weather forecasters for their analyses.
September 20th, 1963. President Kennedy addresses the United Nations General Assembly, proposing cooperation instead of competition in weather prediction and weather control.
It is therefore our intention to challenge the Soviet Union, not to an arms race, but to a peace race.
He proposes a global system of communication satellites to link the world via telegraph, telephone, radio, and television.
Weather satellites were still a touchy dual-use technology. It's a Cold War technology. And so gradually the tide begins to turn, and the United States begins extending invitations to the Soviet Union to collaborate on space experiments.
As East-West rivalries continue through the Cold War, scientists work to transcend that bitter divide.
The Soviet representative, he had a quote about how it was time to think about what the man in the street would value out of the space age. And weather satellites carried this promise for the ability to predict the weather reliably and track hurricanes and track or predict tornadoes. It had significance for industry, it had significance for societies, it had significance for maritime industries, aviation industry. This was something that cut across many different human activities during this time.
The spirit of international meteorological collaboration continues beyond the end of the Cold War. 2006. The Tixi Hydrometeorological Observatory is established as part of a joint Russian-US program. Built on a station initially established in 1932, the Tixi Observatory has kept records on the changing status of the world's polar regions and continues international research to monitor the Earth's changing climate. While the Cold War proved that science could be shared to benefit East and West, one covert area of research is explicitly engineered for destruction: biological and chemical weapons.
Chemical warfare training.
Gases not on our schedule, but you've got to know how to face what they might be cooking up.
In the First World War, every major power employed chemical weapons on the battlefield, resulting in over 90,000 deaths.
So weapons of mass destruction includes nuclear, biological, and chemical weapons. But chemical weapons were seen to be used, and they had a terrible effect in the First World War. And you couldn't control them, not the way you can a rocket or a three-stage rocket or something like that. It didn't have accuracy.
In the Second World War, alternative delivery methods were tested. Germany used Zyklon B, a hydrogen cyanide in gas form, to exterminate Jewish victims on an industrial scale, the largest death toll attributed to chemical weapons. Allied nations such as Canada and the United Kingdom developed biological weapons programs that could destroy enemy crops and harm animals. During this same war, the Japanese tested biological weapons such as anthrax, cholera, and typhoid on thousands of Chinese prisoners of war. Into the Cold War, an arms race of a different kind to that of the nuclear one begins.
While there was chemical weapons, a rather big arsenal, and delivery systems in the Soviet Union. Well, they're developed because the argument was that the Americans are doing the same.
The Soviets and Americans massed enough of these weapons that should they be used, they have the potential to kill everyone on Earth.
Each country had laboratories that developed biological and chemical weapons. The story is that if these pathogens got out there, they would kill millions of people and there'd be no protection against it. I think that's absolutely true. Once you have research, the trick is to weaponize it, and then to find the technologies to deliver it. And during the Cold War, we had efficient methods of delivery.
1943. 80 kilometers from Washington, D.C., in the town of Frederick, Maryland, the U.S. Army sets up a biological warfare research facility known as Camp Detrick.
Here, men have pioneered in the conquest of the Earth's unseen killers.
Research and funding declines with the end of the Second World War, before expanding again with the onset of hostilities on the Korean Peninsula. The United States, fearful of biological or chemical strikes originating from the Soviet Union, begins simulating attacks on unwitting civilian populations. September 20th, 1950. The U.S. begins an 8-day open-air trial of a supposedly safe live bacteria on the citizens of San Francisco, without their knowledge or consent. They spray chemicals in 30-minute bursts, producing a cloud 3.2 kilometers in length, and collect and assess samples from 43 locations throughout the Bay Area. San Francisco residents unknowingly inhale millions of particles of the material released every day throughout the trial. The test concludes that it is entirely feasible to attack a seaport city with biological warfare aerosol. Later, it was discovered that while the bacteria was considered safe, it was responsible for the death of 75-year-old Edward Nevin and the hospitalization of a number of other civilians. 1952. As the Korean War rages, China and North Korea accuse the United States of dropping insects infected with anthrax, cholera, and typhoid throughout the Korean countryside.
Here is an investigating team come to examine a hut in Pechingse district, on the roof of which feathers were dropped by U.S. planes on March the 11th. These flies on the outside of the window of this farmhouse appeared out of season, immediately following low circling flight by U.S. aircraft.
Yet they, like their Soviet counterparts, have the means to conduct an attack and a history of testing. In future warfare, cruise missiles and unmanned aerial vehicles will offer more effective dispersal methods of chemical agents. But in the Cold War, as delivery methods are tested across a multitude of terrains, the Soviets and Americans explore inventive ways to launch biological attacks on both rural and urban populations.
What had changed during the Cold War was the way of delivering these things. You know, you didn't have to deliver them in a tactical way. There are other ways to deliver things. So that made it very dangerous.
May 1955. The U.S. conducts Operation Big Buzz. The test studies the feasibility of producing, storing, and dispersing mosquitoes that could transmit a virus such as yellow fever. They store more than 1 million uninfected mosquitoes over a 2-week period and release over 300,000 from aircraft and ground-release munition systems. They survive the dispersal and are found as far as 600 meters from the test site. The experimentation is considered a success. Similarly, the use of insects to damage food supply crops or infect combatant or civilian populations is examined. February 18, 1956. Georgy Zhukov, Minister of Defense for the Soviet Union, gives a speech at the 20th Communist Party Congress. In it, he suggests a future war with the US will be characterized by the use of weapons of mass destruction, including the use of biological and chemical weapons. The US takes this to mean that the Soviet Union is in possession of these types of weapons, yet concrete intelligence on their nature and volume remains elusive. Within the Soviet military, opinions of the viability of this kind of warfare are mixed.
And their military, Russian military, are very kind of always mathematical. They wanted to have predictability, that if you use 100 nukes, you get that result, you kill that much people. And with germs, you either kill them or you don't. If the weather is sunny, the germs are killed, or if the people wash their hands and put on masks to cover their faces, they're safe. They didn't like it, they didn't buy it. So the initiative was coming from the biological industry, to some extent from the Academy of Science, that they were promoting these weapons, but not the military per se. They wanted predictability.
In the US, fears of Soviet advancements in chemical and biological weaponry leads to a significant policy change. Until this point, any implementation of this technology on the battlefield was permitted only as a response to an enemy's prior use. In March, the National Security Council allows for a first strike of chemical and biological weapons, but only if authorized by the President. The Army's Biological Research Center, Camp Detrick, is renamed Fort Detrick to symbolize the permanency of its mission. And covert evaluations of the effectiveness of biological material on civilians continues across the country. March 14th, 1968. 6,000 sheep are found dead in Utah. The sheep graze in pastures just 43 kilometers from the U.S. Army's Dugway Proving Ground, a facility testing a toxic nerve agent. The U.S. Army deny blame, suggesting death was caused by crop pesticides. Yet later, they pay compensation to ranchers. In the Cold War, as nuclear annihilation threatens the fate of humanity and proxy wars such as the one in Vietnam bloom, the pace of biological and chemical weapons research accelerates, and public consciousness grows ever more aware of the heightened danger of biological and chemical warfare as scenes of the Vietnam War are televised around the world. U.S. support of South Vietnam against the Communist North had been growing steadily throughout the 1950s. Foreign policymakers believe a North Vietnamese victory could lead to further communist gains in neighboring areas.
The Vietnam War, as important as it was to the United States and its allies, and certainly to South Vietnam, was a sideshow in the overall Cold War between the United States and the Soviet Union. It served as a theater for both the United States and the Soviet Union to demonstrate, to try out new technologies.
And in these proxy wars, the technological part of it was always the most important thing, because proxy wars are not about kind of victory in the classical sense. The centers of power of both sides were shielded. I mean, no one bombed America and no one bombed the Soviet Union. I mean, the factories that produced weapons and the scientists who designed the weapons were all shielded. They were not part of the conflict.
January 1962. The United States begins Operation Ranch Hand in Vietnam. The operation's goal is to defoliate the jungle warfare environment, exposing enemy combatants and depriving them of food supplies.
The plane they use is the Provider, or C-123. Each one carries 1,000 gallons of defoliant, which is very like ordinary weed killer in common domestic use in America. It comes in 3 main types: Agent Orange, Agent Blue, and Agent White. If for some reason they're diverted from the DMZ, they can unload it on selected crop targets in other areas held by the Viet Cong.
Between 1962 and 1971, 45 million liters of a chemical agent, Agent Orange, described as an herbicide, is sprayed over the jungles and rural landscape of Vietnam.
It's cost them something like £3 million in weed killer alone. A big bill by American gardening standards, but in Vietnam War terms, only the equivalent of 2 bombers.
This toxic chemical compound strips 24% of the southern Vietnamese countryside bare. A toxic rain that mists down upon populations in over 3,000 villages. A further 28 million liters of agents white, blue, purple, pink, and green are also sprayed. The Agent Orange dose in Vietnam is estimated to be 20 times more powerful than what normal agricultural use requires. The Vietnamese population suffer ongoing health problems including cancer, diabetes, birth defects, and a range of intellectual and physical disabilities attributable to the extensive and extreme use of Agent Orange. As public pressure mounts around the continued use of chemical agents in the Vietnam War, 5,000 non-military scientists sign a petition of concern delivered to U.S. President Lyndon B. Johnson, calling for the U.S. biological and chemical weapons policy to be reviewed. November 25, 1969. U.S. President Richard Nixon renounces the use of offensive biological agents and weapons. He commits to destroy the United States' existing biological arsenal.
So you want to take some of these maybe volatile things off the table. And biological and chemical weapons would have been a natural progression for Nixon to use that as a bargaining chip to lock the Soviet Union into another treaty. Because in those days, Nixon is driven by Kissinger, who wants to lock the Soviet Union into a world in which they have an investment. And taking biological and chemical weapons off the table would have given them a sense of relief. You know, now we can concentrate on something else.
The pledge to not use biological and chemical weapons does not include the use of herbicides, which is added the following year. The final spraying of Agent Orange in Vietnam occurs in February 1971. At Fort Detrick, research into the defense against biological weapons continues. Additional parts of the complex are converted to medical research, such as the addition of a cancer research facility.
Where we have previously had scientists, some of the best people that we could possibly find in the United States, working on weapons of war, we now have scientists devoting their efforts toward saving life rather than destroying life.
The effectiveness of the secrecy surrounding the Soviet biological weapons program yields little intelligence for the United States to have a clear idea of their capabilities. Yet information about the nature of their programs slowly begins to emerge. July 30th, 1971, field testing at a Soviet biological weapons facility, located on an island in the Aral Sea, coincides with an unusual and deadly outbreak of smallpox in the township of Aralsk. For decades, the facility had been testing biological germ warfare agents, including microbial pathogens that cause plague and smallpox. The truth of the incident does not come to light until much later, when it is revealed that a crew member of a research ship became infected when the vessel passed within 15 kilometers of the testing facility. The containment response is swift. 50,000 residents are vaccinated, and travel to and from the port is temporarily suspended. April 10th, 1972, the United Nations opens for signature the Biological Weapons Convention, the first multilateral disarmament treaty banning the development, production, and stockpiling of these weapons of mass destruction. The United States, Soviet Union, and Britain sign. Eventually, over 182 other state parties add signatures. Missing from the Biological Weapons Convention are measures to enforce transparency and the prohibition of continued research. Being unable to inspect biological weapons facilities allows proliferation to continue unchecked. The Soviets and Americans suspect each other of continuing to develop and stockpile biological weapons.
At the same time, you need to have the industry that can mass produce, and you need, of course, delivery systems that will not kill them on delivery. And for that, you need tests, and they were making tests, and that was a gross violation. That was officially acknowledged in the beginning of '92 by President Boris Yeltsin. So we can quote him that really happened.
In the Cold War, a bond is forged between scientists and politicians, earning a rightful position of prestige within the corridors of the Kremlin and the White House. And as science and technology becomes more involved with politics and the military, these create ripples that will live on long after the end of the Cold War. As the Second World War concludes, the American public begin to crave what they missed during wartime rationing: vehicles and appliances. In the early years of the Cold War, American factories once dedicated to military production reconvert to civilian production.
After the Second World War, when, say, the American GDP going on defense reached up to 40%, and then swiftly decreased. But then came the Cold War, and for a long period of time, the United States was spending enormous amounts of money on defense. Russia, most likely in GDP percentage, even much more. It was an unprecedented militarization of both sides, especially the Soviet Union.
As the Cold War continues, government funding elevates science and technology programs which bolster military capabilities and advance political ideology.
And so throughout this time period, you have competing ideas about where should scientific ideas come from? Who should pay for them? Should we primarily fund science that's going to drive military outcomes? Or should we trust the scientists to research whatever they want in hopes that it might be useful later?
January 17, 1961. After 2 terms in office, U.S. President Eisenhower gives his farewell address to the American people.
We have been compelled to create a permanent armaments industry of vast proportions. In the councils of government, we must guard against the acquisition of unwarranted influence, whether sought or unsought, by the military-industrial complex.
And this term gave name to something that scientists had been worried about for most of the 1950s. Some people even call it the military-industrial academic complex. And that the military concerns had really overtaken not only scientific research, but vast areas of the economy. That the United States was no longer paying attention to investing in problems that would benefit the people as a whole. And that instead, so much of industry, so much of university research, that generally the public interest was all being funneled into military research and this conflict with the Soviet Union.
The potential for the disastrous rise of misplaced power exists and will persist. We must never let the weight of this combination endanger our liberties or democratic processes.
Fueled by the Cold War, a military-industrial complex emerges. Private manufacturers bid on lucrative government Department of Defense contracts to manufacture and supply the military with weapons and technology.
So in the 1950s and the 1960s, if you were an entrepreneur, particularly in the tech sphere, your best bet would be to apply for military contracts. This was guaranteed money. You didn't need to worry about finding investors. In some ways, you didn't even need to worry about whether your project panned out. You could get a federal contract, and this would allow you the freedom to develop the ideas that you had proposed. And the government bought into the system on knowing that many of these ideas wouldn't pan out, on the theory that some of them would. And the payoffs for the ideas that did pan out would be worth it.
The manufacture of weapons in both the US and Soviet Union escalates during the Cold War as proxy wars manifest in Korea, Vietnam, and Afghanistan.
Well, I was a scientist in Soviet times. I worked in the Academy of Science. I was not working on defense project per se, but the funding was coming from there. The Russian Academy of Sciences, 90% of its budget came actually from the Russian Defense Ministry. The Russian science, including academic science, was totally militarized. All industry was built double use with a military capability inbuilt. And that's why the Soviet economy was so ineffective. It was uncompetitive. The central planning was used to build it, but it was not the real culprit. It was the entire infrastructure of the Soviet Union was built for a big war.
In the Vietnam and later Soviet-Afghan War, the Soviet Union's military-industrial complex mass produces a tool of war that becomes the most sought-after weapon on the planet: the AK-47, or Avtomat Kalashnikova. Though designed toward the end of the Second World War, the AK-47 revolutionizes warfare. A simple design means affordable mass production. Its sturdy frame just as easily withstands the desert sands of Afghanistan as it does the muddy jungles of Vietnam. In Cuba, Fidel Castro is said to be fond of distributing engraved AK-47s as gifts. The present-day Russian military-industrial complex comprises of roughly 1,500 arms manufacturing companies, employing millions of workers, producing everything from armored vehicles to supermaneuverable fighter aircraft, unmanned aerial vehicles, and ongoing generations of the Kalashnikov rifle.
And still, even today, the Russian leadership, President Vladimir Putin, is implying that if we invest into military and industry, this will have a spillover into civilian. Well, that's not so. In today's world, it's the other way around. It's civilian technologies that are then may be used in military.
Out of the American military-industrial complex during the Cold War emerges a supersonic jet interceptor and fighter bomber, the F-4 Phantom III. Designed and manufactured at McDonnell Douglas, this highly adaptable aircraft is operational in the Vietnam War. Utilizing advanced onboard radar systems, it reaches speeds of over Mach 2 and is capable of carrying just under 900 kilograms of weapons. Similarly, the Soviet Union offer their own supersonic jet fighter and interceptor aircraft. The MiG-21 rolls out from a Soviet Union aerospace and defense company. Though operational since the early 1960s, the MiG-21 stands up against the US F-4 Phantom III.
It was not as technologically advanced as its American counterparts, such as the F-4 Phantom, but it was small and it was nimble. And so it was a very good dogfighting aircraft. And at least early on in the Vietnam War, North Vietnamese MiGs inflicted pretty heavy casualties on US Navy and Air Force pilots.
Out of Soviet and American Cold War military-industrial complexes, mass production of weapons escalates as both nations race to supply former foes and allies with arms. By the 1980s, though some proxy wars of the Cold War era had concluded, the Soviets and Americans were still engaged in bitter rivalry. 1985. US President Ronald Reagan is entering his second term in office.
Under Reagan, the Cold War heated up again through investing in science and technology. But there was a crucial difference from how things had worked out in the 1950s. During the Vietnam era, many universities had actively divested from doing military research. Many universities banned classified research on campus. And so military research was now most frequently conducted by defense contractors. And so when Reagan started investing again in military research, that so much money went to private contractors that we began to call it the Iron Triangle, with the 3 points being defense contractors, the Department of Defense, and Congress. Kind of an impenetrable set of funding techniques that would be resistant to criticism, impervious to expertise, and really impossible to shut down.
While the military-industrial complex builds America's weapons, where they are used, and more importantly sold, is a matter of controversy. Reagan promises to fight communist expansionism. The promise manifests in a deal involving Iran, hostages, American weapons, and a right-wing rebel group in Nicaragua known as the Contras. The Americans seek the release of 7 of their citizens, held hostage in Lebanon by the militant organization Hezbollah, a group with Iranian ties.
There has never been a minute from the first kidnapping on that we've not been doing everything we can. Our great problem is the secrecy, the inability to locate and find. Are they being held by one group altogether? Are they separated? We have reason to believe now from some of our intelligence gathering that they are being moved around.
Senior officials within the Reagan administration facilitate the sale of 1,500 missiles to the Khomeini government of Iran for a total of $30 million. Despite an arms embargo on the sale of weapons to Iran, officials hope that in exchange for the weapons, the Iranian government will negotiate the release of their citizens. When news of this breaks, Reagan initially denies any negotiations with Iran.
Our government has a firm policy not to capitulate to terrorist demands, that no concessions policy remains in force. In spite of the wildly speculative and false stories about arms for hostages and alleged ransom payments, we did not, repeat, did not trade weapons or anything else for hostages, nor will we.
He retracts the statement a week later.
The principal issue in contention was whether we should make isolated and limited exceptions to our arms embargo as a signal of our serious intent. I considered the risks of failure and the rewards of success, and I decided to proceed, and the responsibility for the decision and the operation is mine and mine alone.
Following an investigation into the weapons deal, it is discovered that $18 million of the funds are missing. Lieutenant Colonel Oliver North of the National Security Council comes forward to take responsibility for covertly diverting the funds to the Contras in Nicaragua. The Contras are engaged in efforts to overthrow the socialist Nicaraguan government. They are funded, trained, and supplied with weapons from the United States. Eisenhower had warned of the potential rise of misplaced power and the unwarranted influence of the military-industrial complex over a democracy devoid of public scrutiny. In the United States as of 2017, about 10% of the $2.2 trillion in factory output is dedicated to the production of weapons that are then sold to the Defense Department and used by the U.S. military. The ongoing legacy of the military-industrial complex can still be felt in the Russia of today.
And so when the Soviet Union collapsed, this resource industry separated itself from the defense industry that it should have served and began to sell it all on the world market. And a whole generation of Russian oligarchs made billions of dollars, first selling the reserves that the Soviet Union had accumulated, and then selling the new production. This experience of the Cold War, it's imprinted in the infrastructure of the country. We still have bad roads, but good railroads, because the railroad system was the main strategic logistical system for a war. Everything moved by railroad. Tank divisions would be moved from one theater or one part of a theater to another by railroad.
As of 2019, the United States and Russia remain the two largest suppliers of weapons throughout the world. The Cold War helped launch the atomic bomb and realize the potential energy of nuclear power. Once lesser scientific fields, seismology and meteorology, redefined and elevated humanity's understanding of the Earth, weather, climate, air, and atmosphere. Superpowers pushed to develop some of the most lethal biological and chemical weapons known to exist. As the military-industrial complex rose like a behemoth during the Cold War, the scientific community rose in stature within the corridors of power. But since the end of the Cold War, the international scientific community has been notably absent from those corridors.
So with the end of the Cold War, the fall of the Berlin Wall, the collapse of the Soviet Union, the US-Soviet competition stopped. And that driving force behind US technological development really lessened. So for the first 10 years after the end of the Cold War, the United States was essentially unrivaled. It was very difficult to make the argument that the US needed to develop more advanced technology. And then after the 9/11 terrorist attacks, we found ourselves in a different situation where we were dealing with transnational terrorism and where our qualitative advantage really didn't matter as much.
Yet, the lessons of the Cold War left a lasting impression on the way we look at science and technology.
In the United States, the legacy of the Cold War is all around it. We see it in the internet. We see it in contaminated soil and water left over from nuclear production sites. But we also see it in the institutions of science in the United States. Institutions like the National Science Foundation that continue to fund basic research in the United States came directly out of a Cold War context. This language that science should be free, that funding should be generous, that scientists should focus on basic research continues to animate much of the ways that we talk about science and technology today.
In the Cold War, information is power. In a bid to outdo each other, the Soviet Union and the United States of America conceive of new ways to obtain information that will see them gain an edge in technological supremacy.
So there's a certain kind of existential threat that the Cold War forced upon the military and compelled it to act in ways that produced, almost by accident, the underlying communication infrastructure that we see today.
Data collection manifests through espionage, deception, and invention.
There were Russian specialists gathering information on new American ways of warfare to produce countermeasures.
High-altitude spy planes and space satellites observe military maneuvers and state secrets. Global communication networks and espionage technology will go on to inspire the future technology of the digital age. The Cold War, a decades-long struggle between two superpowers and former allies, the United States of America and the Soviet Union. But beyond the ideological divide of capitalism and communism was a battle of another kind, one for technological supremacy.
And for each of these systems, science and technology were critical for how they were going to thrive and grow and bring prosperity and justice for their people.
Experimentation with nuclear power, innovation of weapons technology, exploitation of science capabilities.
The entire space program, you could argue, was a creature of the Cold War.
A race for scientific supremacy that lifts humanity beyond Earth's atmosphere, drags the world to the brink of nuclear annihilation, and launches decades of research into scientific and engineering marvels that continue to define the modern world. Gathering intelligence on an enemy has been a feature of war throughout the ages. But in the Cold War, information gathering offers military and ideological advantage. It means being able to develop nuclear weapons, intercontinental missiles, and supersonic jets. Being able to gather information or not could mean the difference between victory or defeat. In an age before high-tech surveillance, it is people who are relied on for intelligence gathering.
Most people, I've found, are fascinated by spies and spying, but for the most part it's fairly dreary, painstaking and frustrating work. But the point is, of course, with human intelligence, every so often, very rarely, but every so often, you get a tremendous payoff.
In the race to develop atomic weapons, Soviet spies embed themselves in nuclear weapons research and development programs in Canada, the United Kingdom, and the United States.
So in the late 1940s, the United States had an atomic monopoly, meaning it was the only country on Earth that had its own atomic weapon. And for military leaders, this was a secret that had to be guarded. They did this through classified information. They did it through security background checks. They did it through loyalty oaths. The smallest bits of political activism could get you flagged and not allowed to get a security clearance.
Despite these measures, the Soviet Union is successful at infiltrating the United States project to build the world's first atomic bomb. August 1944. Klaus Fuchs begins work in a theoretical physics division at the Los Alamos laboratory.
If you look at Klaus Fuchs, he was an idealistic young man. He'd seen what Nazism could do. He joined the Communist Party just before he left Germany, went to Britain, got a very good education in physics. When he was posted to start to build the atom bomb, he could see the tremendous effect this would have on the balance of power in the world. And he wanted the Russians to also know about this.
1 month later, Fuchs is present at the Trinity test site and witnesses firsthand the destructive power of the atomic bomb.
I always thought the great irony is that once the bomb is tested at Trinity, the so-called gadget, President Truman, the new president, who didn't know a damn thing about the bomb until he became president, he walks up to Stalin at the Potsdam Conference and says, "We have a new weapon we're going to use against the Japanese." And Stalin looks at Truman and he says, "I hope you use it well." What Truman didn't realize is that Stalin had complete knowledge of what was going on at Los Alamos and the Manhattan Project. He probably knew more about the atomic bomb than Harry Truman did.
Stolen and smuggled blueprints and other top-secret plans accelerate the development of the Soviet nuclear weapons program.
To build an atom bomb is a very complex theoretical and practical undertaking. And the sort of information that the atomic spies got back to the Russians was general plans on how to build the bomb, but most importantly, it was how to avoid going down rabbit burrows that didn't lead anywhere.
In August of 1949, the Soviet Union detonated its first atomic weapon. And when that happened, the Americans assumed that it must be because of espionage. And the intelligence operatives weren't wrong. There was significant espionage in the US atomic program.
January 1950. Klaus Fuchs confesses to being a Soviet spy. This leads to the uncovering of more conspirators, such as husband and wife Americans Julius and Ethel Rosenberg.
As Julius Rosenberg and Morton Sobel, convicted of revealing atomic secrets to the Russians, enter the federal building in New York to hear their doom. Another of the spy ring, Mrs. Ethel Rosenberg, who with her husband was convicted of actually transmitting the secrets to Russia through Soviet diplomatic channels.
Julius and Ethel Rosenberg are the first American citizens to be executed for espionage. Done by electric chair at New York State's Sing Sing prison in 1953. Early information collected during the Cold War relied on spies, feet on the ground. But as technology advances, the use of high-altitude reconnaissance planes becomes an important way of gathering information during the Cold War. August 1st, 1955. In an area that would become known as Area 51 in the Nevada desert, aircraft manufacturer Lockheed tests their top-secret experimental spy plane. The single-engine high-altitude reconnaissance aircraft, the Lockheed U-2, colloquially known as Dragon Lady, is designed to gather intelligence through day and night at an altitude of 21.3 kilometers. An aircraft that can reach this height is thought to be able to avoid Soviet missiles and radar. With a light airframe weight and glider-like wings, the U-2 relies on a specially formulated jet fuel that will not evaporate at high altitudes.
U-2 was fielded on the belief that it would only be effective and only be operational for a handful of years before the Soviets caught up and figured out how to shoot it down. As a matter of fact, the U-2 is still in service today, so it actually really exceeded its expected life.
To gather intelligence, the U-2 is equipped with radar, antennas, and imaging equipment, including a large format camera capable of high-resolution photographs from high altitudes. The U-2 is a modular aircraft. Its payloads and intelligence-gathering equipment can be swapped out and the interior refit for specific missions. May 1st, 1960. A U-2 launches from Peshawar, Pakistan, to begin a flyover of the Soviet Union. Its pilot is Francis Gary Powers, and his mission leads to one of the most dramatic moments of the Cold War.
Francis Gary Powers was tasked with investigating the possibility that the Soviets were fielding intercontinental ballistic missiles at a location known as Plesetsk. So in other words, Powers went on his mission to try to figure out whether there was a missile gap or not.
The aircraft is detected by Soviet air defenses, and a Su-9 scrambles, attempting to bring down the American aircraft. The mission is abandoned when they fail to intercept the U-2. The American spy plane flies on, now passing above a Soviet surface-to-air missile battalion. The Soviets have another chance. This time they seize upon it. A V-750 VN missile is deployed from the Soviet S-75 high-altitude air defense system. The missile zeroes in on the spy plane, detonating behind the U-2, damaging its tail and wings. Francis Gary Powers is lucky to escape, parachuting away before a second missile strikes. The information-gathering advantage that America momentarily had plummets as the aircraft scatters in ruins on the outskirts of the Soviet township Sverdlovsk. And now the Soviets have two important information sources: the captured pilot and the wreck of the U-2 spy plane. One they interrogate, the other they study.
On display in Moscow, what's alleged to be the wreckage of the U-2 spy plane, which Russia claims to have shot down by rocket.
A public trial for Powers follows.
It's the Hall of Columns in Moscow, scene of many a previous Russian trial. And now, Francis Gary Powers, pilot of the American U-2 spy plane shot down over Russia, faced the judges with composure. He behaved with dignity throughout his ordeal, though his life was possibly at stake.
August 19th, 1960. Francis Gary Powers is convicted of espionage and sentenced to 10 years of confinement. 3 in prison, the remainder in a labor camp. Had the US-built Blackbird SR-71 been operational for Francis Gary Powers' mission into Soviet airspace, things might have turned out differently.
With a mind towards Soviet countermeasures, Lockheed and the Air Force and the CIA developed the SR-71 as a high-flying, fast strategic reconnaissance aircraft. The next step in the competition after the Soviets figured out how to shoot down the U-2.
Developed as a black project, one that is unacknowledged by government, military, personnel, or contractors, the Blackbird SR-71 holds the record as the highest and fastest flying, air-breathing manned aircraft on Earth.
Living up to their motto, peace through surveillance, by providing information for the security of the United States and the free world. The SR-71 in a single flight has flown over 15,000 miles. On one mission, it is capable of mapping a section of the world equal to a path 60 miles wide from San Francisco to New York.
Axial flow turbojet engines power the SR-71 to a cruising speed above Mach 3. It can do this at altitudes above 24.3 kilometers. The SR-71 avoids missiles in a very simple way, by accelerating. However, flying at such high speed and altitude increases atmospheric friction, which may heat the fuselage to melting point. For that reason, the aircraft is built from a lightweight and heat-resistant material, titanium. And in the Cold War, the largest supplier of this rare material is America's superpower rival, the Soviet Union. Now, the Americans resort to classic Cold War subterfuge. They establish offshore shell companies, which they use to purchase large amounts of titanium, which they export back to Area 51 in Nevada. Several weeks prior to the Blackbird's maiden flight, and after 2 years in a Soviet prison, U-2 pilot Francis Gary Powers is released as part of a prisoner exchange program between the US FBI and the Soviet KGB.
The shootdown of Powers' U-2, his capture, his subsequent show trial, led to a suspension of overflights of the Soviet Union. So it would fall upon the development of reconnaissance satellites to carry on that strategic reconnaissance of the Soviet Union.
A new kind of warfare is harnessed, one in which communication, observation, and photo reconnaissance satellites watch, listen, and learn. July 1st, 1957. The start of the International Geophysical Year.
One of the most ambitious programs for international scientific cooperation during the Cold War was something called the International Geophysical Year, or IGY for short. It actually lasted 18 months instead of a year. It involved nearly 70 countries who cooperated to gather information about the natural world.
A period where Cold War tensions briefly thaw, and scientific and technological innovation proves that the Soviets and Americans possess advanced technological capabilities.
When we talk about the IGY today, one of the reasons we remember it is because the IGY was what led to satellites. Both the United States and the Soviet Union said that they would attempt to launch an artificial satellite during the IGY.
In May of 1957, those charged with the United States satellite program determined that small satellite spheres would be launched as test vehicles during 1957. The first of these test vehicles is planned to be launched in December of this year.
But as the eyes of the world look skyward, it is not an American achievement they witness. October 4th, 1957. The world's first artificial satellite, Sputnik, is launched by the Soviet Union. At 58 centimeters in diameter, the aluminium sphere completes an orbit of the Earth approximately every 98 minutes.
Sputnik 1, or as it was called, SP, or Sputnik First, or PS, Простой Sputnik. It was really a very simple satellite. In terms of technical complexity, it is comparable to school satellites that are now built in some classrooms. At the time, it was a first. It was important as a demonstration that humans can do something more than simply reach space.
The world's population looks up as Sputnik tracks through Earth's lower orbit, passing above suburban homes. A faint radio signal, a Soviet heartbeat in space.
All round the world we listen. All round the world it makes headline news.
As the political theorist Hannah Arendt once observed, the launch of Sputnik meant that for the first time humans could observe like God down upon Earth itself, from outside of itself. We were an observer observing our own world for the first time.
The space era started with the satellite, because humans learned not only to launch something very high up, but also how to get something out to the near-Earth orbit, and to leave it in space for quite a long time, and to use it in some ways. For example, not a lot of people know, but the signals of the first satellite acted as a practical demonstration of the possibilities of the employment of satellite navigation systems. So it's GPS, GLONASS, Beidou, Galileo, everything that is now created. All this was born from the first satellite, from those beep-beep signals that were heard by radio lovers in those years from the sky.
The United States' efforts to launch their own satellite were hampered by inefficiencies in the development of rocket systems.
At least until Sputnik, the United States really refused to centralize or even plan its scientific priorities. But also inter-service rivalries between the different military agencies meant that in the mid-1950s, the Army and the Navy and the Air Force were all working on their own rocket systems. And one consequence of this was that the Soviet Union beat the United States into space.
Following the launch of Sputnik, US President Eisenhower looks for a response.
And immediately, President Eisenhower looked around and said, who do we have? What have we got? Eisenhower wanted to do something more civilian than not. He looked at the Navy and their Vanguard rocket, which was somewhat civilian. It had a scientific purpose, even though it was a Navy rocket.
Now there's explicit pressure on the labs who had developed payloads to put on the Vanguard satellites to accelerate the development of the Vanguard satellites. They were moving as fast as they considered responsible when dealing with a cutting-edge technology.
December 6, 1957. Vanguard Test Vehicle 3 launches from Cape Canaveral.
A moment or two of high expectation after the firing button has been pressed.
It rises approximately 1.2 meters into the air before the engines lose thrust and it explodes on the launch pad.
The world was watching in anticipation of the US matching the Soviets in this technological capability. Instead, Vanguard goes up in flames. The launch vehicle collapses onto the launch pad. The satellite actually went bouncing across the tarmac. And so, in addition to being a big technological disappointment to scientists and engineers, this is also a geopolitically significant event that's viewed as a symbolic failure on the US's part.
Although a public embarrassment, rocket launches are still a fledgling technology, developing at a breakneck pace.
We must learn to expect in the United States that we cannot have success every time we try something new in a complex scientific field. We have our work cut out for us. We are behind now in the satellite field. We will not stay that way.
So in 1958, the US launch success rate is 48%, and in 1959, it goes up to 51%. So It's understood that these are cantankerous systems, an unprecedented level of complexity in which you have a one-time shot at getting all of this right.
With the failure of the Vanguard rocket, America looks to one of their other programs in development. This one under the guidance of Werner von Braun, who with his team at the Army Ballistic Missile Agency have been working on launch systems based on the German V-2 rocket technology.
They'd taken that Nazi war rocket and actually built it and expanded it and made it bigger. It was capable of putting a satellite into space. It was capable of putting a satellite into space a year before. They just hadn't been given the go-ahead. So as soon as they said, can you do it in 60 days? They said, we can do it in half of that. And within a very short amount of time, Explorer 1, the Americans' first satellite, was launched into space by that German team.
January 31st, 1958. The Explorer 1, designed and built at the Jet Propulsion Laboratory in California, is successfully launched by a modified Jupiter C rocket.
We may be sure that a great sigh of relief accompanied the Explorer as it soared away into outer space, exactly according to plan.
The first U.S. satellite in space is equipped with instrumentation to measure the radiation environment in Earth's orbit. It discovers that two donut-shaped radiation belts, trapped by magnetic fields, loop around the Earth. These belts, now known as the Van Allen radiation belts, are named after Dr. James Van Allen, who along with his graduate students at the University of Iowa, designed the instrumentation for the satellite. This discovery provides important data for later space research and is considered a major discovery during the International Geophysical Year. March 17th, 1958. Vanguard Test Vehicle 4 successfully launches the Vanguard 1 satellite. The Vanguard project may have been unsuccessful in its original goal, but with the successful launch of Vanguard 1, it can lay claim to another milestone. Today, it is the oldest satellite in Earth's orbit.
Vanguard 1 is still in orbit, and I believe that the last estimate was that it'll remain in orbit about 600 more years.
With Sputnik, the Soviet Union has won the race for the first satellite in Earth's orbit. But it sets an important precedent the United States plan on using to their advantage.
And in some ways, Sputnik wasn't entirely a disaster for American leaders because it established the right of overflight, which the Americans wanted so that it could conduct high-altitude surveillance, either through U-2 airplanes or later through reconnaissance satellites.
As the Cold War plays out and technology launches humanity skyward, communication technology changes the way information can be harvested. Satellites are soon equipped with television and photographic capabilities. They become eyes in the sky.
So there was a nascent military intelligence program, hadn't been quite approved. In fact, it was the first thing approved after Sputnik. Eisenhower approved a program called Corona, which is launching a camera with recoverable film pods.
The Corona project had been approved by President Dwight Eisenhower in 1958, but moves forward rapidly following the shooting down of Francis Gary Powers' U-2 spy plane. Conducted under the cover of the Discoverer program, the United States Air Force tells the public that these satellites are gathering data on environmental conditions from space.
Discoverer 13 roars aloft from a California launching pad. It's lucky 13 because after 17 orbital passes around the Earth, the missile's payload, a data capsule, is dropped to Earth and recovered.
The true purpose of the project is to launch reconnaissance satellites intended to photograph areas of the Soviet Union inaccessible to spy planes. August 19th, 1960. Discoverer 14 launches into polar orbit. It carries a single panoramic camera and 9 kilograms of film.
They took images of the Earth's surface, and then they ejected these capsules with the film, and those capsules were recovered mid-air by aircraft. Capsules had parachutes on them, and it was the job of the aircraft with a big cable device on the front of it to snatch those capsules as they were descending out of mid-air.
They're trying to catch a capsule parachuting down from Satellite Discoverer, and the men in the flying boxcar succeed at the second attempt.
During its 17 orbits of the Earth, Discoverer 14 covers more than 2.4 million square kilometers of Soviet territory and produces more images than all earlier U-2 missions combined. Over the course of its 12 years, the Corona program takes over 800,000 images from space, providing vital intelligence on sites associated with ballistic missiles and nuclear energy.
Interestingly, this knowledge meant we need not overreact to conjectures about threats, but rather expend our defense resources more realistically.
The advent of reconnaissance satellites certainly gave the United States a greater understanding of the Soviet Union. It did away with the perception of a missile gap, for example. It gave us better understanding of Soviet research and development. It allowed us to monitor the size of the Soviet nuclear arsenal.
Corona is now history. It stands as an important point in time. The first, the longest, and most successful of the nation's intelligence programs to date. Corona explored and conquered the unknowns of space reconnaissance. And it opened the way for more sophisticated follow-on systems.
Images, data, surveillance, vast tomes of information are now transmitted via communication satellites. During the Cold War, information is conveyed, collected, and captured through technological innovation. Military-funded research programs and the rise of computer technology combine to change how information is gathered and distributed. Prior to and during the early years of the Cold War, computers used by the military were bulky and cumbersome. ENIAC, or Electronic Numerical Integrator and Computer, analyzed ballistics vulnerability and lethality at the United States Ballistics Research Laboratory. It is considered the world's first electronic digital computer. What would take a scientist a day to calculate, ENIAC achieved in less than a minute. Operational from the mid-1940s to the mid-1950s, ENIAC programs included calculating the feasibility of thermonuclear weapons, instrumental during the research and development phase of the hydrogen bomb. A mass of vacuum tubes, resistors, capacitors, and electronic components that weighed over 25 tons, ENIAC took up 167 square meters of space and consumed 150 kilowatts of power to function. It may have been quick to calculate, but this Goliath of a machine took weeks to program. Similarly, EDVAC, or Electronic Discrete Variable Automatic Computer, was operational at the United States Army Research Laboratory by the start of the Cold War. While reprogramming ENIAC was labor-intensive, often taking weeks, EDVAC's design revolutionized computer efficiency because it utilized a stored program concept. This computer did not require constant input and updating of instructions. Its data and programs are built into the computer's memory. EDVAC's stored program concept revolutionized and inspired the design architecture of computers from the Cold War era to the modern day. A single computer is a powerful tool at the start of the Cold War, but the next step is to expand the ways to collect, absorb, and distribute information over multiple locations.
Computer networks were central to the development of the Cold War technological mindset. But computer networks in particular came around in the mid-50s, 60s, and 70s as a kind of attempt to secure a nation. Right? The computer itself as a unit is foundational to what the information age needs, namely computational processing power. But the capacity to connect those computers gave many of the Cold War superpower strategists the affordance or the opportunity to connect at a distance, and to take actions at a distance.
1949. The United States, concerned that the Soviet Union has developed their own atomic bomb, looks for a system to warn of any incoming Soviet long-range bombers. If a bomber can reach the US, it could potentially be carrying an atomic weapon.
Cold War technological projects were ambitious. They were expensive. They were innovative, and they were transformative, with lasting consequences for years to come. One of the most impressive was a project called SAGE for semi-automatic ground environment. SAGE was a project developed out of a lab associated with MIT called Lincoln Laboratory that came out of early computing.
SAGE divided the United States into 8 sectors, and each of those sectors was divided into 32 subsectors. And the SAGE system was all about gathering information from various sensors, from radar, from other types of sensors, bringing that information together, making sense of it, so that decision makers could respond. So in the event of an actual Soviet attack, you could launch interceptors, you could launch surface-to-air missiles, and you could launch US bombers to make sure that they weren't destroyed on the ground by a Soviet attack.
1952. Funded by the United States government, MIT selects IBM to develop and build the computer that will be the brains of SAGE.
You are listening to the heartbeat of the SAGE computer. Every instrument in this room is constantly monitoring, testing, pulse-taking, controlling.
The AN-FSQ-7 computer weighs 250 tons and is made up of over 55,000 vacuum tubes, 175,000 diodes, and 13,000 transistors.
It is really 2 computers, but only one is operating the system. The other, with the same vast memory, performs as a slave.
The total system takes up an entire floor of approximately 2,000 square meters. Each computer can operate 50 monitors or workstations, track up to 400 airplanes, and communicate with up to 100 radars, observation stations, and other sources of information. This set of data combines to give a complete picture of what's happening in US airspace.
The SAGE system was a technological success. It was quite impressive the way SAGE integrated data from all sorts of different sensors, brought it together, made sense of it. But in the end, it was a strategic failure because it came into being just as the ICBM appeared. And so the problem was no longer merely a Soviet bomber attack, but it was a Soviet ICBM attack. And SAGE really couldn't do anything about that.
Namely, SAGE is the space where we see a number of the really concrete, specific innovations that we recognize today as foundational to computing coming to life. We see the monitor, or at least the photographic heads-up display. We see the development of peripherals like mouse and printer that connect and how those inputs and outputs work. We see the really critical attempt to build and share files so that files would be shared and stored simultaneously on different spots. That's fundamental to a communication system. And it's all stuff that began thanks to this ultimately aborted and short-lived, but nevertheless colossal investment of state funding in national communication network infrastructure.
A monumental undertaking costing more than the Manhattan Project. The technology developed from SAGE goes on to form the basis of the first real-time airline booking system.
SAGE was enormous. At one point, half of the country's programmers worked in SAGE. SAGE was in some ways both a way to develop programming and a college to train American programmers. Many of the things that we associate with 1950s computing or later computing, things like real-time airline reservations or visual displays, parallel processing, all of these ideas were developed directly from SAGE.
As computing technology continues to advance, so too do ideas of ways to distribute information over a linked computer network.
So this kind of communication grid, communication infrastructure through computer networks might mean that generals could communicate in the event of a nuclear attack. It might mean that they would be able to automate or launch in the event of an attack from the enemy a nuclear retaliation. Right? In many cases, the earliest attempts to found a national computer network follows from the existential military mandate to secure the nation in the event of an attack, to make it survivable.
1959. Paul Barron joins the RAND Corporation and works on a survivable computer network he believes will allow for continued communication in the event of a nuclear attack.
Paul Barron realized in part, they needed a communication infrastructure that could be struck down at any moment, that would still be able to function if only 1/3 of it remained.
Barron works on an idea of dividing up information into what he calls message blocks before sending them out across a network. 1965. Donald Davis at the National Physical Laboratory in the UK independently comes to the same solution as Paul Barron. He refers to his idea as packet switching.
Now, packet switching protocols are fairly straightforward. Effectively, you take the message that the sender wants to send to the receiver, you break it up into a number of packets, effectively envelopes. You stamp each envelope with the address to which it's going to be sent, and you send them all off. And those envelopes or packets can go under any pathway. They can follow a random walk. They can go anywhere they want across this distributed system. All that matters is that they arrive at the right destination. And so long as they arrive at the right destination, the protocol will reorder the envelopes in the right order, open them all up, and reassemble your message for you. And the brilliance of this packet-switched protocol is that it allows for any part of the system to be disrupted.
The Advanced Research Projects Agency, or ARPA, builds upon the ideas developed by Barron and Davis when they look to share information across computers in multiple locations across the United States. October 29th, 1969. ARPANET, the Advanced Research Projects Agency network, goes online. Initially, the network connects computers between 4 locations: research laboratories at UCLA, Stanford, UC Santa Barbara, and the University of Utah.
The important thing to remember when we're thinking about why the ARPANET came to be is that it doesn't have a single purpose. Namely, it never had one mandate. Instead, part of its brilliance is that it solved the question of how to do computer networking without ever providing or precluding or assuming anything about the why. So of course there were really practical reasons scientists wanted to collaborate and share data over a distance one with another. But that's a purpose they could have accomplished by other means. And what the ARPANET really stands out for, I think, is its kind of generative openness to the many purposes that we as users continue to bring it today.
ARPANET's software and network capabilities expand to include remote login, file sharing, and the ability to communicate via electronic mail.
It completely erases the meaning of space. We can connect here and be very close to people who are all over the world.
From the Cold War, ARPANET evolves into today's internet, an infinitely tentacled global, high-speed communication network.
The vision is to have a superhighway with all the information passing for all the entertainment, for business, for all our academic institutions, for the social infrastructure of this nation.
Even though the ARPANET goes on to found several very specific things that are important for the internet later, I think it's really just this kind of open imagination of the network that is most seminal, that is most influential in how we think about the internet today.
Not all projects during the Cold War tech race had successful outcomes. In the Soviet Union, independent to advances in the United States, computer engineers were also working on the idea of computer networks.
It's clear that intelligence agencies knew about, in the roughest terms, the networking attempts of the other side. But beyond those basic, acknowledgement of the concurrence of networks, there doesn't appear to be much in the way of concrete details, or especially influence. So I think what we have here is a fascinating example of how similar ideas kind of exist in the ethos and pop up in different places, but often at the same time.
Soviet developments had suffered setbacks due to the divide between civilian and military research projects.
The relationship between civilian and military interests in the Soviet Union is famously one of separate silos. For example, one of the earliest computing network pioneers, in fact, the man who first imagines and proposes a civilian computer network, was initially a military researcher. His name was Anatoly Ivanovich Kitov. And he thought, well, wait a second, why don't we apply this computing resources to a public question, namely, how do we manage the economy? How do we make the economy better so it hurts fewer and so it's more efficient and more optimal? And for this rather sensible and indeed kind of subtle proposal, he got himself in much trouble.
Kitov's plan is intercepted by his military supervisors and is criticized for suggesting that military resources should be shared with civilians. His proposal results in the end of his military career, and the following year, his Communist Party membership is revoked. 1962. Viktor Glushkov, a mathematician, attempts to succeed where Kitov failed.
The ORGAS project is perhaps the most ambitious attempt to build a computer network that the world has ever known. It stands for the All-State Automated System, and its purpose was singular and simple: to save the planned economy. Namely, it sought to usher in what we might call electronic socialism, or the attempt to bring the sluggish, paper-bound stacks of quotas and factory mandates and commands from the government and through factories up into the digital age, or at least to the electronic age. Namely, this computer network would have a central computing center in Moscow that would be the command and control, basically the brains of the operation. And that mother node, as it were, would connect to the second level, where as many as 200 prominent computing centers would be found throughout major cities. And then those 200 computing centers would then extend down into the third level, as many as 20,000 factories, enterprises, basically imagine like a computer input system for uploading and downloading the commands across the command economy.
Viktor Glushkov's plan, ahead of its time, faces opposition from Soviet leadership, who feel it threatens party control over the economy. In 1970, 8 years after the initial proposal, it is denied funding.
If we were to sum up in short why there was no Soviet internet, I would argue that computer networking first took place in the US thanks to well-regulated state subsidy and well-managed research collaboration between universities and government. Whereas you see simultaneous attempts to develop computer networking in the Soviet Union break against the rocks of unregulated competition among bureaucrats and ministers and internecine fighting. In short, I think we can see that networking first took shape thanks to capitalists behaving like socialists, not socialists behaving like capitalists.
The Soviet Union's unsuccessful attempts to develop a computer network were not the only projects that ultimately failed to live up to their potential. In the latter stages of the Cold War, US President Ronald Reagan looks to go beyond early warning systems such as SAGE and its successors. March 23, 1983. In a televised address, Reagan calls upon the scientific community to develop new technology to combat potential Soviet nuclear strikes.
I call upon the scientific community in our country, those who gave us nuclear weapons, to turn their great talents now to the cause of mankind and world peace, to give us the means of rendering these nuclear weapons impotent and obsolete. Tonight, I'm taking an important first step. I am directing a comprehensive and intensive effort to define a long-term research and development program to begin to achieve our ultimate goal of eliminating the threat posed by strategic nuclear missiles.
Ronald Reagan, I think, is justifiably seen as a Cold Warrior, but he also really abhorred nuclear weapons, and he actually had a vision of a world without nuclear weapons. And so for him, the path to get there involved the development and deployment of highly reliable defenses against ballistic missiles.
The Strategic Defense Initiative, or SDI, is an ambitious plan to develop a range of technologies designed to detect and destroy Soviet intercontinental and submarine-launched ballistic missiles before they reach American shores.
And his advisors suggested, why don't you do space-based lasers? Many of his advisors came from the aerospace industry, they came from the defense industry, they came from defense contractors. And they said there's a real opportunity here for safety and for our industry if you mounted lasers and other kinds of weapons on top of satellites. Or maybe you could have a giant mirror-based system that could somehow reflect lasers at incoming weapons. But either way, somehow you would use a super high-tech, space-based system to counter nuclear attacks before they arrived.
Critics and the media give Reagan's Strategic Defense Initiative another name.
Then along came President Reagan's Strategic Defense Initiative, sort of an awkward name, so SDI got a nickname.
It was typically called Star Wars, especially by its critics.
I'm sorry that anyone ever used the appellation Star Wars for it, because it isn't that.
Now, most credible scientists thought this was ridiculous, and they said it was ridiculous to Congress. They wrote editorials, they gave interviews saying Star Wars will never work. But by the 1980s, there were very few of these critical scientists actually had access to the halls of power as they had in the 1950s. So the defense contractors assured the president that yes, Star Wars would work.
The research and development of laser-based defense systems are not new. The Lawrence Livermore National Laboratory's Excalibur project was in development prior to the president's call to the scientific community to develop these new defenses. Project Excalibur, under the guidance of theoretical physicist Edward Teller, a key contributor to the development of the hydrogen bomb, plans to use a nuclear blast to power X-ray lasers that will target and destroy Soviet missiles. Initially designed to be deployed in space, it is later planned to launch from submarines when a Soviet strike is detected. The project goes through a series of tests with disappointing results and is eventually cancelled. Its legacy, a symbol of the impracticality of the Star Wars program. The Soviet Union did not mount a parallel defense system in response to SDI, instead continuing to fund advanced missile systems they hope will render it obsolete.
Even short of that ambitious goal, SDI promised to impose lots of costs upon the Soviet Union, to force the Soviets to change their nuclear posture and to move away from the things that they did well and they were comfortable with doing, such as large ICBMs, and towards other parts of their posture where they had greater challenges. What we now know is that as the Soviet leadership contemplated SDI, they were confronted by the technological gap between the United States and the Soviet Union. And they had to ask themselves whether the Soviet economy, Soviet society was capable of closing that gap or not. And in the end, they realized, I think correctly, that was impossible.
Although the promise of SDI was never realized, not all elements of the program failed. Today's ground-based mid-course defense, or GMD, is based on technology developed as part of the wide-ranging research done on the Strategic Defense Initiative. During the Cold War, information was power. Today, global communication networks built on the technology developed during the Cold War are a part of everyday life. We live in a high-speed, hyper-connected environment. The Internet of Things connects digital devices across both civilian and military industries. Society connects via smart households, cars, and domestic appliances.
But now, when we are ordering pizza, or when we are getting a cab or an Uber ride, we are using the results that were made possible by our satellite, Sputnik. Of course, no one remembers it. No one thinks about it now. But it's a fact. Those beep-beep signals made getting hot pizza into our homes today possible. Such an interesting interweaving of times, from what was 60 years ago and what is happening right now.
Militaries, too, engage in warfare, using artificially intelligent weapon systems, unmanned aerial vehicles, global positioning systems, and communication satellites. Now more than ever, information is power, and it's at our fingertips. For centuries, human beings looked skyward for inspiration. When astronomers first gazed towards the stars, planets, and moon, our world opened up.
If you've reached the highest peak and you've gone to the deepest depth, what's next? What's next is space, the high frontier.
It is during the Cold War that Earth's atmosphere is breached, and we enter the uncharted domain of space.
Even though cosmonautics is often presented as a search for knowledge and scientific exploration of the world, in reality, the defining factor that promoted the development of this technology was the competition between two political regimes.
The technological advances we saw in the space race only happened because of competition between the US and the Soviet Union, no other reason.
The Cold War race to space, a launching pad for humanity, the future of technology and space exploration. The Cold War, a decades-long struggle between two superpowers and former allies, the United States of America and the Soviet Union. But beyond the ideological divide of capitalism and communism was a battle of another kind, one for technological supremacy.
And for each of these systems, science and technology were critical for how they were going to thrive and grow and bring prosperity and justice for their people.
Experimentation with nuclear power, innovation of weapons technology, exploitation of science capabilities.
The entire space program, you could argue, was a creature of the Cold War.
A race for scientific supremacy that lifts humanity beyond Earth's atmosphere, drags the world to the brink of nuclear annihilation, and launches decades of research into scientific and engineering marvels that continue to define the modern world.
The space programs of the United States and the Soviet Union in the late 50s on through the 60s was one of intense competition for the hearts and minds of the rest of the world.
The competition involved defining goals that could be reached first. I mean, it was a race to do things first. And in order to do them first, you needed particular technical capabilities.
There was a race, competition, demonstration, domination of one over the other. And of course, those investments that were made into cosmonautics at the time defined the development of space exploration to the present time.
The Cold War race to space might launch in the 1950s, but it is ignited during the Second World War through the development of nuclear weapons and missile technology.
Technology only advances when there's a reason for it to advance. We have cars, we have trains, we have phones, we have computers. For a reason, they affect our everyday life. Giant space rockets, not so much. There has to be a specific reason for that to happen. So really the only reason that we saw enormous rockets being developed in the 50s and 60s was one, that they could carry nuclear missiles. The other reason was space exploration.
During the war, German scientists and engineers developed the V-2 rocket, a long-range guided ballistic missile, the world's first. As the war nears its end, the Soviet Union and the United States both look to exploit this technology and those who made it in their own weapons programs.
Well, the role of the German scientists after World War II was very different in the United States and in the Soviet Union.
If we're talking about the Soviet Union, then it's more about the technological heritage. That is, the factories, the production facilities, the technologies of the rocket engine that the Soviet Union managed to bring over. They played a part in the development of the Soviet cosmonautics. But our cosmonautics moved away from the German heritage pretty quickly and started to work on their own.
You know, at the end of the war, the Soviets grabbed as many scientists as they could, German scientists. The British and the Americans grabbed as many scientists as possible, too.
At the top of the US list is Wernher von Braun, Germany's leading rocket scientist, an instrumental figure in the development of the V-2 rocket.
In World War II, the German scientists were the experts in rocket technology. They actually created the first rocket capable of reaching space. Wasn't powerful enough to stay in space, but it could reach high enough to be in space. The sad thing is it was built as a Nazi war weapon created through slave labor for really bad reasons, killing civilian populations in the West. After the war, it got used by both countries, the US and the Soviet Union, to create space rockets and nuclear missile carriers.
May 2nd, 1945. Werner von Braun surrenders to the United States Army. He is recruited as part of Operation Paperclip and later sent to the United States with other German scientists.
During the early post-war period, as an example of their patchwork, they mated this old warhorse V-2 out of Peenemünde, Germany. The V-2 Whack Corporal combination was America's first two-stage missile. It also marked for the first time the blending in action of American and German rocket brains, a combination that was destined, despite many setbacks, to have its rendezvous with history.
In the early years of the Cold War, the first challenge is not to launch a human into space. It's to launch a man-made object, a satellite. October 4th, 1957. The Soviets gain an important victory with the launch of Sputnik. Pressure mounts within the United States to respond with all available resources.
There were lots of contending ideas of what the United States should do. Eisenhower established the President's Science Advisory Committee to help him define the program and ask them, what should we do in space? Of all people, Richard Nixon, then Eisenhower's vice president, was a leading advocate for a separate military and civilian program, and Eisenhower accepted that, and that's where NASA came from, as a separate civilian space agency. So there was an intense period of both technical and organizational development in the year following Sputnik.
Before sending human beings into space, scientists experiment on other non-human life forms.
In these days of heightened animal rights awareness, we forget how different the 50s and 60s were. And I think it's natural at that time for the scientists to think, before we risk a human on a launch pad, let's send an animal first, even if that means the animal is not going to come back. Not really something we could imagine doing today.
November 3rd, 1957. Sputnik 2 is launched from the Baikonur Cosmodrome. Like Sputnik 1, it features radio transmitters and telemetry equipment, but unlike its predecessor, it also houses the first animal sent into Earth's orbit, a dog named Laika.
So it was the beginning of life sciences in space. At that point, the Soviet Union hadn't figured out how to provide life support to get a living organism like a dog back to Earth, and so the poor animal died rather quickly. Obviously, if you start sending dogs, it's only a matter of time before you start sending other living creatures and eventually humans.
When America looked at doing the same thing, it decided to send chimpanzees, which have a lot in common with humans, maybe more than dogs in some ways. They intended to bring the chimpanzees back. Not all of the primates that were sent on space flights did survive. Some weren't capable of even surviving the primitive life support systems they had on the pad before the rocket launched.
The scientific purpose is to gauge how space travel affects living organisms. The experiments allow scientists to develop technology that will one day support human life in space.
It only took a few moments to extract Sam, the spaceman. They found him alive all right, apparently none the worse for his far-flung adventure.
At the end of the 1950s, both nations have shown they can reach space. Now, they set their sights upon a target, Earth's moon. April 12, 1961. The Soviets launch Vostok 1 and become the first nation in history to launch a manned spacecraft into orbit. From the Soviet Baikonur Cosmodrome, the Vostok 3KA space capsule is launched by a modified R-7 rocket.
The earliest astronauts were well aware that they were sitting in a little tiny capsule on top of fundamentally a converted intercontinental ballistic missile. I mean, these are the same rockets that were poised to set off a nuclear war.
All of these rockets were designed to carry nuclear missiles. That meant they had rockets capable of carrying really heavy things. When it comes to putting somebody in space, having a rocket that can carry a lot heavier, all of a sudden puts you at a huge advantage.
The Vostok 3KA space capsule is 2.5 meters in diameter, spherically shaped and weighs slightly less than 2,500 kilograms. Inside the capsule is Soviet cosmonaut Yuri Gagarin, the first man in space. The Vostok spacecraft sends Gagarin on a 108-minute orbit around Earth, over which he has little control. Traveling at almost 27,500 kilometers per hour, Gagarin's re-entry is also controlled by a computer program. The space capsule receives and transmits radio commands before maneuvering back into the Earth's atmosphere.
The craft was auto-controlled, but Gagarin had the control lever. In case of emergency, he would switch to manual control to turn the craft around using the brake engine. This started with Gagarin, and it continues to be this way. In our country, rockets were built by rocket engineers, and for the rocket engineer, it's important that the rocket works, regardless of what it's transporting. So the human control was perceived as a backup, at first as a useful component, and then as a backup means of manual control, if auto-control can't handle it.
When Soviet leaders release information about this historic first in the space race, they do not include one particular piece of information related to the landing.
Because he had a steeper ballistic descent trajectory, and the speed of entering the dense atmospheric layers was higher, the deceleration had a higher impact on the cosmonaut. The last stage of descent had quite an original solution. The craft landed separately, and the cosmonaut was separated from the craft by the ejection seat.
So the Russians had another big secret to keep, which was the international rules for the first person to fly in space were very specific. You had to take off and land in the same vehicle. That was a huge secret. They kept that secret for about a decade because it broke all those rules. At the end of the day, it didn't really matter. A human went into space and came back.
The symbolic victory the Soviets claim by launching the first satellite and the first man into space puts additional pressure on the United States to respond.
Kennedy decided the United States had to respond and wrote a memo to his advisor saying, identify a space program which promises dramatic results in which we could win. And those requirements drove the technology to find a winning program, which was going to the moon. So Project Mercury was basically, let's get a person up there and see what happens. Whether they can function, whether they can survive, whether they can do anything, do any tasks. So it was basically a very rudimentary, very preliminary look at the ability of humans to be in space and operate in space.
May 5th, 1961. Just 1 month after Gagarin's orbit, American astronaut Alan Shepard becomes the second man, yet the first American, to enter space, aboard Freedom 7.
They were 3 weeks away from sending that first person into space. You think about all the epochs of human history that people thought about spacefarers, and the actual divide was 3 weeks between the two superpowers. But first is first and second is second.
Lasting about 15 minutes, Shepard's suborbital space journey projects him to an altitude approximately 200 kilometers above the Earth, where he reaches speeds of 8,260 kilometers per hour. His Project Mercury spacecraft is powered by Redstone rockets, ballistic missiles that have now launched American satellites, animals, and man into space. May 25th, 1961. Newly elected President John F. Kennedy announces that America will send a man to the moon and return him safely to Earth by the end of the decade.
I believe that this nation should commit itself to achieving the goal, before this decade is out, of landing a man on the moon and returning him safely to the Earth.
When it came to science and technology, one of the biggest differences between the Eisenhower administration and the Kennedy administration is that Eisenhower wanted to fund science and technology for a specific defense outcome. He wanted useful objects, whereas Kennedy was much more interested in the prestige of science. He was much more interested in a hearts and minds approach to science and technology.
Pretty much the only reason that both superpowers were doing the space race was for headlines and propaganda. They were fighting a war on the front pages of countries around the world who were choosing which superpower to go with in terms of which philosophical communism or capitalism, which superpower they were going to back.
For the Soviet Union, cosmonautics was very important, not just from the technical or scientific standpoint, but as a means of propaganda. So it was important not so much what technology Americans had, but to see when they are planning to achieve what. And the goal was to do it faster and earlier. And this sense of rush characterized Soviet cosmonautics.
July 1st, 1961. The Army Ballistic Missile Agency is formally transferred to NASA, creating the Marshall Space Flight Center. Von Braun is appointed the center's first director, allowing him to oversee and influence advances in rocket technology, including the development of a super booster launch vehicle. June 16th, 1963. The Soviets launch Vostok 6 and claim another first. On board is the first female to enter space, Soviet cosmonaut Valentina Tereshkova, orbiting the Earth 48 times over 71 hours. Tereshkova spent more time in space than the combined duration of American astronauts up to that point in time.
So the Soviet Union had female rights as one of the important subjects at the time. And partially, there was some real efforts to make that happen. But partially, it was a means of propaganda. But really, to take the decision to have a woman in space, to entrust her with this opportunity, in the Soviet Union, it was made possible a lot earlier than in the USA.
When NASA comes looking for its first astronauts, it doesn't put a gender requirement on the application form, but the only people who have the experience and qualifications to fly advanced jet testing, which is what NASA needed for its pilots, were men. Women were not excluded from gender by NASA, they were excluded by the society that wasn't allowing them to fly, particularly the military. It started a conversation that lasted for a long time. It took a long time for things to change. It was really the mid-1970s and early 1980s that we first saw women going through the military test piloting schools, first as engineers, then as pilots, that allowed them to obtain the same qualification level that the men had had.
Ever outdoing each other, the race to space is fever-pitched, and the Soviet Union continued to achieve a number of space firsts. March 18th, 1965. Soviet cosmonaut Alexei Leonov exits the two-crewed spacecraft Voskhod 2 via an inflatable airlock.
To make the first venture into open space possible, it was necessary to develop at least 3 separate technical systems. First of all, the spacesuit that would allow a person to survive in open space. An airlock was needed to perform the procedure, and you also needed to prepare the spacecraft for it.
The closest analogy is, if you've ever seen a bounce house at a children's party, those big inflatable castle things, the kids jumping up and down on it, that's kind of what they designed as an airlock. They put it snug against the side of the spacecraft, launched it into space, and when they were in space, they inflated this thing, so now you have a 2-hatch process. You can climb into an inflatable tunnel in the middle, close one hatch, open the other one to open space, come in and out. It was pretty risky, but they were able to do that. This is the first time humans have ever been outside in space.
Alexei, get ready to enter. On orders from the ship's commander Belyaev, Leonov pulls in on the lifeline and approaches the airlock.
When Alexei Leonov, the first spacewalker, finds himself outside in space in 1965, he immediately runs into issues nobody knew what was going to happen. He got back to the hatch of the spacecraft only to find his spacesuit was too inflated, he couldn't actually get back in.
The spacesuit used for spacewalks is a separate system. It's basically a separate human body-shaped spacecraft that is mobile, so it's really a very complex system.
So he had to do something quite dangerous. He had to reach down to his chest and start operating a valve to bleed the air out of his own spacesuit. Now, if you've ever heard about what divers go through when they get the bends and they're coming back from scuba diving, you know there's a great danger of bleeding the pressure out of something like that. You can cause yourself nitrogen bubbles in your bloodstream and it can kill you. That was the risk he was going to take. He gradually bled the air out of his spacesuit down below the level that was safe, but it got his spacesuit deflated enough he was able to get back inside the hatch and close that hatch.
Satellites frequently travel within a low Earth orbit of 2,000 kilometers or less. Manned spacecraft, such as Vostok 2 and Freedom 7, operate in low Earth orbit and suborbital space, less than 200 kilometers above Earth. The average distance to the Moon from the Earth is 382,500 kilometers. To get there and back safely, the Soviets and Americans must be inventive.
We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
When Kennedy said on May the 25th, 1961, I believe we should go to the moon, we really didn't know how we were going to do that.
When you watch those old 1950s science fiction movies, that was kind of how America imagined going to the moon. Take a huge, big rocket with big landing legs, land it in one piece on the moon, and then everybody climbs down a big ladder, explores the surface, climbs back up the ladder, comes back in one piece to Earth.
And then von Braun and his team said, it's really too big a jump from where we are now. So let's find things we can do with slightly smaller rockets, which is to rendezvous around the moon, lunar orbit rendezvous, and have specialized spacecraft, one spacecraft to go from Earth to lunar orbit, and a second spacecraft only to go from lunar orbit down to the surface and back.
A lunar orbit rendezvous is considered the concept exhibiting the best chance of taking a human to the moon and returning them to the Earth. A main spacecraft is launched and remains in lunar orbit. It is the command module. Attached to it is a second auxiliary service module containing fuel cells and propulsion systems. A third lunar lander, or excursion module, is used to descend to the surface of the moon after detaching from the main spacecraft. After redocking, the service module powers the main spacecraft back to Earth. The lander module is left to drift into the void of space or crash down to the surface of the moon.
But it gave people kind of the willies, because it meant that the mission success depended on the ability to dock, to rendezvous and dock in orbit around the moon. And if you somehow missed, the people in the lunar lander, the two astronauts, weren't going to come back.
November 9th, 1967. Apollo 4 is launched by the Saturn V.
The Saturn V was a product of von Braun and his team. It was a very scaled up version of the V2 rocket. The choice of the lunar orbit rendezvous mode meant that the spacecraft could be light enough to be launched by one big rocket, Saturn V, with 5 engines in its first stage.
These F1 engines, clustered at the bottom stage of the 3-stage launch vehicle, are capable of generating 3.4 million kilograms of thrust, and are the most powerful engines ever created. Each engine has a turbopump, moving more than 160,000 liters of propellant per minute, feeding RP-1, a type of kerosene, and liquid oxygen into a combustion chamber through 6,300 holes, each the size of a drinking straw. Here, the fuel and liquid oxygen mix and are exposed at just the right moment to an ignition source. The upper stage is launched using liquid hydrogen, capable of propelling heavy payloads, including 3-person crews, into space. Though Apollo 4 is an unmanned test flight, it guides the direction that NASA will take to the moon. Both the Soviet Union and the United States suffer setbacks, rocket failures, and the deaths of astronauts and cosmonauts. But the pace of the race barely falters, and the Soviet Union begins to realize they are falling behind. They hope their new lunar program, approved in 1964, will put them back in front. Part of this program is a launch system similar in conception to the Saturn V.
And they understood that they needed to catch up. And for some time, they tried to develop this super heavy rocket, N1. The spacecrafts were tested, including those that meant to land on the moon. they didn't manage to make it fly. It was launched 4 times, and 4 times it exploded. And unfortunately, at that time, the phrase, "we are shooting with cities," was very relevant, since every launch of an N-1 rocket was tens of unbuilt high-rises in terms of cost.
Further testing of Apollo's spacecraft continues, with Apollo 5 in January of 1968. September 14th, 1968. The Soviets launch Zond 5. It is the second spacecraft to travel to the moon and circle it, but the first spacecraft to do this and return safely to Earth. The US believed the Soviets are closer to achieving the first manned lunar orbit than many thought possible. NASA has to act. The Apollo program ratchets up. They launched their first crewed flight, Apollo 7, on October 11, 1968. While Apollo 7 remains within Earth's orbit, Apollo 8 does not. December 21st, 1968. Apollo 8 takes astronauts Frank Borman, James Lovell, and William Anders beyond Earth's low orbit. For 3 days, these astronauts orbit the moon. They are the first human beings to do so. The first that America achieved with the Apollo 8 manned flight was a propaganda victory over the Soviet Union. But in the first 6 months of 1969, the race accelerates again. Soviet and American spacecraft testing intensifies. However, the Soviet space program begins to suffer a series of technical setbacks. Each one puts them at greater distance from the lunar surface. Between January and June of 1969, half a dozen Soviet spacecraft either fail or fail to launch. But the Soviets do achieve another remarkable first that lays the foundation for the future evolution of manned space stations. January 1969, Soyuz 4 and 5 are launched.
There's 1 person in one spacecraft and 3 in the other. They're in space at the same time, and then they dock in space, and they don't have a hatch in the middle that's capable of somebody just floating through from one to the other. What has to happen is somebody has to spacewalk. So they have 2 people come out of the 3-person spacecraft and spacewalk over to the other one. And this is the first time in history, and it's still a very rare thing, that people come back home in a different spacecraft than they launched from. But they proved that this can be done, and it was a step on the way to the moon for the Soviets.
Following the manned lunar orbit by Apollo 8, a low Earth orbit is undertaken by the crew of Apollo 9 in March of 1969. This flight, 2 months after the Soyuz docking, is designed to test the lunar module while operating as a self-sufficient spacecraft or when maneuvering for docking. On the 4th day of a 10-day mission, lunar module pilot Russell Schweikart climbs out from the Apollo 9 module and walks in space. The objective of his spacewalk is to test the life support system of the NASA spacesuit. If it supports life in space, it's reasonable to assume it will do the same on the lunar surface. The end of the 1960s decade is only months away. Kennedy's declaration of landing a man on the moon and returning him safely to Earth echoes through the corridors of NASA. May 18th, 1969, Apollo 10 launches.
Apollo 10, man's second journey to orbit the moon, was a full-scale rehearsal of all of the activities required to land men on the lunar surface, except for the actual landing.
You couldn't do lunar orbit rendezvous until you got to the moon. So the first mission to send the whole spacecraft complex to the moon was Apollo 10 in May of 1969, which was basically a dress rehearsal for the lunar landing.
This is the first time an Apollo spacecraft orbits the moon with a complete crew. Without setting foot on the lunar surface, Apollo 10 completes its objective, and NASA are ready to fulfill the promise of setting man on the moon. July 16th, 1969, at 9:32 a.m.
20 seconds and counting.
Apollo 11 lifts off from the Kennedy Space Center in Florida.
T-minus 15 seconds. Guidance is internal. 12, 11, 10, 9. Ignition sequence starts. 6, 5, 4, 3, 2, 1,
0. Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11.
On board, Commander Neil Armstrong, Command Module Pilot Michael Collins, and Lunar Module Pilot Edwin Buzz Aldrin. At NASA Command, former German rocket scientist Werner von Braun and his colleagues watch on. The V-2 ballistic missiles that Hitler had unleashed in World War II, the antecedents of the Saturn V rockets, now take men to the moon.
Man sets off on his first journey to a specific destination in space, to a target in tranquility 250,000 miles away.
4 days after launch, on July 20th, 1969, an estimated 650 million people watch as the lunar module touches down on the surface of the moon.
Listen, Tranquility Base here. The Eagle has landed.
Roger, Tranquility. We copy you on the ground. You got a bunch of guys about to turn blue. We're breathing again. Thanks a lot.
The Soviets claimed so many firsts throughout the 1960s. But now, the United States has done it. Neil Armstrong steps down from the lunar module onto the moon's surface and says,
"That's one small step for man, one giant leap for mankind."
Soon after, Edwin Buzz Aldrin follows him.
Beautiful view. Isn't that something?
Michael Collins watches on from the command module.
Roger, it was a beautiful job, you guys. And don't forget one in the command module. Roger.
July 24th, 1969. Astronauts Armstrong, Aldrin, and Collins are retrieved from their re-entry capsule after splashing down in the Pacific Ocean, just months before the decade expires.
We hope and think that those people shared our belief that this is the beginning of a new era. The beginning of an era when man understands the universe around him, and the beginning of the era when man understands himself.
50 plus years after Apollo 11, we're still debating its significance. In terms of Kennedy's intention of signifying U.S. technical leadership, U.S. political will, I think it was a total success.
Days after Neil Armstrong steps onto the surface of the moon, a small bunch of flowers and a note are placed on President Kennedy's gravesite at Arlington National Cemetery. On the note is written, "Mr. President, the Eagle has landed." The 1960s are over. The moon landing is a technological and ideological victory for the United States, but it took years to achieve and cost billions.
The budget for the Mercury, Gemini, Apollo programs peaked at 4% of the federal budget. In 1975, Richard Nixon made the decision that NASA should now be just a normal agency. So he removed it from the special status and made it like Health and Human Services. The budget dropped to about 0.5% of the federal budget, and it's been there roughly ever since.
There was one goal when Americans went to the moon: to surpass achievements of the Soviet Union. Basically, to surpass the flight of Gagarin. Not because there was a practical necessity. The only practical necessity was to show that American science, American industry, and after all, the American way of life is cooler than the Soviets. That's it.
All of these things lined up. And I think that's why it hasn't happened again, because what are the chances of all those things lining up in history? We always have the money. We always can make the technology if we want it. We can always make a presidential speech. In fact, how often do presidential speeches actually come true? Statistically, pretty small. Everything had to come together, and it did, and then it evaporated.
Now that the United States successfully answered Kennedy's call to land man on the moon, it's up to President Richard Nixon to decide what's next for space exploration.
And his answer was not much. He became convinced that there was no value in continued human exploration. He did not see it as an element of Cold War competition the way John Kennedy had.
Meanwhile, the Soviet Union shifts focus.
After the successful moon landing, there were 2 reorientations in the Soviet program. The first one is that the piloted program was reoriented towards the long-duration orbital stations, so-called DOS. And this program kept developing up to the fall of the Soviet Union, and still exists on the International Space Station. Its foundation was created at that time, after the moon program of the USA, or maybe even during the moon program. And the second direction was automated stations, exploration of the moon with machines, as it was called at the time. The word robots was not as popular.
April 19th, 1971, the Soviets launched Salyut-1, an unmanned, pressurized, multi-compartment spacecraft, the world's first space station. 2 months later, in early June, Soyuz 11 successfully docks with Salyut-1. The crew remained there for a further 23 days, orbiting the Earth 383 times. For the Soviets, this is another first, the longest duration a manned spacecraft has remained in space. The 21.4-meter-long space station provides the cosmonauts with 100 cubic meters of living and working space.
Again, it was a big propaganda thing to finally have a space station in orbit with people working on it. Live television images were beamed around the world. People got to know the crew, got to know them quite well because they watched them for weeks up there, felt quite attached to them.
Their return to Earth is expected to be a triumphant celebration, but then tragedy strikes.
And what happened? During descent, the hatch that was supposed to open later opened. And instead of letting the atmospheric air into the craft, it let the atmospheric air out. It was in the upper levels of the atmosphere, and for the human body, it was basically a vacuum.
Everything was automatic from that point on. Nobody on the ground knew that anything was wrong. The spacecraft came down, the parachutes opened, it landed in the middle of the Soviet Union, and the rescue teams came out and opened the hatch and found 3 people inside as if they were fast asleep, and they were all dead. They were the only people to have actually died in space. Other people have died on the way to or from space, but this is the only crew who ever died in space.
After this rescue, spacesuits were introduced, which cosmonauts and astronauts are still using today.
By 1973, NASA's Apollo program has wound down, and they are repurposing Apollo technology for use in their space station program, Skylab. May 14th, 1973, NASA launched their first space station, but it almost ends before it begins. 63 seconds after launch, as a Saturn V rocket propels the unmanned Skylab's 100 tons toward orbit, a micrometeoroid shield designed to protect Skylab from space debris prematurely deploys, then tears away from the station. Failure of the micrometeoroid shield means Skylab no longer has thermal protection. Without thermal protection, the interior temperature will rise to unbearable levels for the crew and cause damage to instrumentation and equipment. Mission Control notes that Skylab's solar arrays, essential to providing energy to Skylab, do not deploy as pre-programmed. On Earth, NASA delays the launch of the Skylab crew, quickly training them for a revised mission to repair Skylab. The Skylab crew launch 10 days later. Additional crews launch in the months that follow. Soviet and American space stations pioneer a new frontier in space exploration, solar and stellar astronomy. They enable research to be conducted in space over extended periods of time. And they are the perfect platform from which to observe Cold War adversaries. Unknown to the international community, the Soviet Union is running 2 concurrent space station programs. One civilian, the Salyut stations. The other, Project Almaz, is a military project.
For the long-duration orbital stations, the military component was the priority, at least in the beginning, even though in the public eye, they were called consistently Salyut.
To mask their true nature, the Almaz stations are given Salyut designations. The first Almaz station, Salyut 2, is launched April 3rd, 1973.
And Almaz was basically a piloted spy satellite and a piloted military station. Even in the Cosmonautics Museum in Moscow, there is a huge photo camera, probably the biggest photo camera in the world, not counting the astronomic telescopes. It's a film camera, the purpose of which was to spy on Americans and other friendly and not so friendly nations over which these stations would fly.
But the Almaz program also brings something new to the space domain. June 25th, 1974. The Soviets launched Salyut 3, also known as Almaz 2. It is equipped with a 23mm anti-aircraft cannon, the Richter R-23. This gas-powered rapid-fire cannon can be fired remotely as the module orbits. If the Americans target the Soviet space station, the Soviets have the capability to strike back. Though that never occurs, it is alleged the Soviets did test-fire this cannon in space at the conclusion of the final space station mission. If this is correct, it earns the Soviet Union another first: the first nation to fire a weapon in space. By the mid-1970s, the surface of the Moon has been reached, walked upon, and driven across. The Soviets and Americans have launched hundreds of satellites into Earth's orbit, transmitting vast amounts of data about the Earth, its atmosphere, weather, and changing climate across an array of terrestrial communication networks. The Soviets and Americans endure setbacks with space station construction. Experiments prove that humans can function in space for long durations. In proxy wars such as the Korean and Vietnam Wars, these Cold War enemies remain at a distance, but in the closing stages of the space race, they are provided an opportunity to move closer together.
Richard Nixon, as he considered what to do after Apollo, had what he called a pet idea, which is flying non-U.S. people on U.S. space missions. And so he pushed on NASA to open up its program for non-U.S. participation. And then he wanted to find areas of détente with the Soviet Union to lower the tensions between the two countries. And so those two things combined to the idea of using leftover Apollo hardware to do a joint mission.
July 15th, 1975. Soyuz 19 launches from the Baikonur Cosmodrome, Kazakhstan, with cosmonauts Alexei Leonov and Valery Kubasov. Hours later, from NASA's Kennedy Space Center, an Apollo module lifts off, carrying astronauts Tom Stafford, Deke Slayton, and Vance Brand. The Apollo-Soyuz mission is the first cooperative Soviet-American space mission where two separate flights rendezvous in space. Orbiting the Earth over 2 days, the Soyuz capsule and Apollo Command and Service module align, 225 kilometers above the Atlantic Ocean. 20 years before, populations gazed skyward, trying to locate the Soviet satellite Sputnik. Now, across the world, millions of people tune into a televised broadcast as the American Apollo module and the Soviet Soyuz meet in space. On July 17th, 1975, at 12:12 p.m., the Soyuz and Apollo vehicles achieve a hard dock. Just a few hours after docking, at 3:17 p.m., hatches between Soyuz and Apollo are opened. Commanders Alexei Leonov and Tom Stafford greet each other in a profoundly simple and humane way. They shake hands.
In space, it became a demonstration of the improving relationship between two opposing superpowers. A space handshake, as it was then called. Soyuz Apollo was a good ending to the moon race, the moon program in general. It was the finale for the Apollo program and the end of the moon race for both countries.
Though the Cold War continued on Earth for a further decade and a half, this one moment symbolized the benefit of scientific, engineering, and human collaboration. The relationship between the Soviets and Americans would ebb and flow throughout the decades. Eventually, they are joined in space by many nations, all sharing a desire to push farther into the space domain and populate it with military and civilian satellites. Initially launching in 1998, the International Space Station today lists over 15 participating countries involved in ongoing space exploration projects. It is a feat of engineering that would not have been possible if not for the Cold War.
Right now, we have the International Space Station. It was built by shuttles that were created during the time of the space race. The Russian segment is constructed from modules, the technology of which is based on the Soviet space station technology, which was also a product of the space race and Cold War.
There's a space station up there that's as big as a football field, and it's bolted together by humans, Americans and Russians, and it comes over once every 90 minutes. If you know where to look in the night sky, you can see it come over as the brightest star in the sky many nights. That is a monument to human imagination and ingenuity, but it's also a monument to cooperation, because the countries that started developing that in the 1990s are very different countries than we see now. And we see a lot of tension between current America, current Russia, and yet that space station keeps going, people still keep cooperating in space. So that's a beautiful capstone for the space program. It's the one thing that's holding everybody together.
Space is now populated with satellites, spacecraft, and ongoing projects from numerous countries across a multitude of industries. Private space companies such as SpaceX and Virgin Galactic continue the race to space, exploiting its potential across industries as diverse as mining and tourism. The legacy of the space race lives on in those that were inspired by the achievements of both the Soviet Union and the United States.
In Russia, every Soviet kid dreamed of becoming Gagarin, dreamed of becoming a cosmonaut. Some of them, of course not all, went on to get higher technical education. And at the moment, the Russian economy is largely based on those engineers and on those specialists who grew up during the time when Gagarin was worshipped, when Gagarin was a national hero.
The main impact of the space program was to motivate people to study science and technology. It led to the stockpiling of the technical base of this country and many other countries. And it pushed areas of technology like miniaturization.
If you're trying to understand which part space plays in our lives, look at your cell phone, your smartphone. The camera in it comes from space, because initially, all these technologies were created in order for a small digital camera to be placed on a spacecraft. All this was created in the 70s and 80s, and ultimately became cameras in our phones.
The race to space during the Cold War was a launch into the unknown, reshaping ideologies and extending our knowledge of Earth and our solar system.
The biggest things that the space program have given us are the things that weren't to do with technology, but to do with how we see ourselves. When Apollo 8 went out to the moon, they went around the far side of the moon and saw things that no human eye had ever been able to see. But that wasn't what they learned. What they learned was as they came around the moon, they saw the Earth rise. And they saw the planet that we're on, 250,000 miles away, this little blue marble in the vastness of space, so tiny that they could put their thumb out at arm's length and completely cover over everywhere they'd ever been, everybody who'd ever lived or died, all on that tiny little point of light. And they realized how fragile it is where we come from and how much we need to preserve this planet. These are things that you don't plan for in an engineering textbook. We see our planet in a way that no ancestors ever could imagine.
Like lessons learned on Earth, the space domain presents ongoing challenges. Laws governing how space can be explored, populated, and dominated will influence how future wars might play out and act as a way to preserve space and our Earth's environment. The race to space continues into a domain as limitless as the imagination that dares to explore it.